Can everyone hear me? I guess it's okay. Okay, hello everyone. Welcome to the first presentation of this seminar. This presentation will go about solid behavior in flow reactors. First, I will give a small introduction. Then I will explain my research aim. Afterwards, I will show some results. And at last, I will have a small conclusion. But first, here you can see my title of this presentation. And I've highlighted flow reactors in continuous operation. So for the moment, there are two main operations that our chemical reactions are performed in, and are batch reactors and flow reactors. Let's zoom first into a batch reactor. A batch reactor is just a vessel with a stirrer. You put your products inside, you set the temperature, and then you'll have your chemical reaction that is performing inside that reactor. But what are the advantages of the batch reactor? They are flexible. It is not designed for one specific reaction. It is easy in operation. It has high volumes per cycle. A batch reactor has a volume of several cubic meters, and it is easy in cleaning. But there are also disadvantages. You have batch-to-batch variations. Each run you need to add the reagents, you need to set the temperature, set the stir speeds, and so on. Therefore, you have variations in your product quality. A batch reactor is also limited in reaction pressure and temperature, and the heat transfer is not efficient due to a low surface-to-volume ratio. Then we have the flow reactor. The flow reactor is for a continuous operation. The advantage of a flow reactor is that it has an advanced heat and mass transfer due to a higher surface-to-volume ratio. It can also have, it is also the possibility to reach high temperatures and pressures, and you will downsize the reaction zone. Then this is very important when you are performing reactions with high concern or high risks. The disadvantages of a flow reactor is that you will have residence time distribution, you will have difficulties with solids, viscous and immiscible liquids, and there is a hard temperature control, especially when you're performing exothermic reactions. Then I have highlighted heterogeneous solid-liquid reactions in my title. So Robert et al. Has researched more than 80 chemical reactions, and he concluded that 50% can benefit from flow technology. He also divided that 50% into three types of reactions: type A, B, and C. Type A is the very fast reactions, type B the rapid reactions, and type C the slow reactions. But he also discovered something, and he discovered that 63% of them struggles with the presence of solids. But why do we want to research heterogeneous solid-liquid reactions in flow? First, we wanted to apply and research the more extreme reaction conditions, and afterwards we'll also look to process intensification. We can use ultrasound, microwave energy, photochemistry, and so on. But yeah, like I told, the main challenge is the presence of solids in flow reactors. The solids can cause sedimentation, fouling, and clogging. Sedimentation, you can see in the green, is just that a particle will sedimentate towards the bottom of the tube due to a gravitational force. Fouling is that a particle will stick towards the wall due to a wall-particle interaction. And clogging is just a blockage of the tubing. The consequences of sedimentation and fouling is that you will have differences in resonance time distribution of the particles, and sedimentation and fouling can lead to clogging of the reactor. If you have clogging of the reactor, then you will have blockage and you can have rupture of the tubing, and this will lead to a shutdown of the process, which is not okay. If you're working with heterogeneous solid liquids feeds in a flow reactor, then you can have 5 different flow regimes. You can see the 5 different flow regimes on the right. Each flow regime has also a velocity profile and a concentration profile, which you can see here on the left. If we now zoom into the homogeneous regime, then you can see that the particles are divided uniformly over the whole reactor. You can also see at the top, towards the velocity profile and the concentration profile, that they also are symmetric. If you then look to the pseudo-heterogeneous and the heterogeneous flow regime, then you can see that the particles are more concentrated towards the bottom of the tube, but they are still divided over the whole tube. And then if we look to the sliding bed and the fixed bed, then you can see that all the particles are concentrated towards the bottom of the tube. If we look to the velocity profile of the fixed bed, then you can see at the bottom we'll have a velocity of 0 at the bottom with a fixed bed. Then for the moment in literature, you can find some existing formulas that can calculate a speed to prevent sedimentation of particles. I have highlighted here the first formula that has been published, and that's from Durand. And Durand has made a formula based on the minimum pressure drop. If you will have a slurry inside your reactor and you will apply different speed of flows, then you will have a minimum pressure drop. And that speed, that is valid for that formula. But there is a problem with this formula. This is only valid for the mining industry. And the mining industry has other geometries than the milliflow reactors. So therefore, it is not applicable for the milliflow reactors. Then there are also in literature some possible reactors or techniques which can handle solids. And I've highlighted here one, the pulsatile flow. And I've highlighted it because this is the technique that I will use in my research to prevent sedimentation of solids. And why pulsatile flow? You can see with pulsatile flow in the graph that the velocity is not a fixed velocity, but it is in the form of a sinus wave. And the advantages of pulsatile flow is that you will have increased mixing, reduced fouling and sedimentation, and it is usable with high reaction pressures. So this was my introduction. So now we move on to the research aim. So the first research aim is that we wanted to determine the solid behavior. And we will do this with a high-speed camera. With the high-speed camera, we can have a look towards the concentration profiles of the suspensions, the velocity profile of suspensions, and we can determine the flow regimes. And at last, we will also look to the influence of the pulsator on sedimentation of particles in milliflow reactors. With this knowledge then, we can develop a flow reactor which can handle solids, and at last, we can optimize and scale up a solid-liquid reaction. But in this PhD seminar, I will only look to the determination of the solid behavior. So then we move to the results. So I will discuss 3 different results: the concentration profile, the velocity profile, and the influence of the pulsator. So let's first have a look towards the concentration profile. Here you can see the setup of my concentration profile. You can see that we use a beaker with the suspension in. Then we have a centrifugal pump to pump the suspension in the tubing. I will use PFA tubing. And then we'll also use a glass tube. Why a glass tube? Because this is transparent, and this is the reason why we use a glass tube, so we can work with a high-speed camera to look towards the suspension inside the reactor. Here you can see on the right, you can see an example of a picture made with the high-speed camera with the glass beads. So then here you can see some results of the concentration profiles. You can see results from glass beads with 57 micrometers, and at the top you can see the different flow regimes. So let's take a look at the highest flow rate, 914 milliliters per minute. If you look to the picture, then you can see that the particles are homogeneous divided over the tube. So we have a homogeneous flow regime. That's the reason why also in the concentration profile set this as a standard value. If we then further lower the flow rate towards 590 milliliters per minute, then you can see that we have a deviation of the standardized concentration profile, and this means that we will have a pseudo-heterogeneous of a heterogeneous flow regime. If we then further decrease the flow rate towards 481 milliliters per minute, then you can see on the picture that the particles are more concentrated towards the bottom of the tube. And you can also see in the concentration profile here that we'll have the formation of a layer. And this indicates that we will have a sliding bed or a fixed bed flow regime. If we then further decrease the flow rate towards 384 milliliters per minute, then you can see that almost all the particles are sedimentated towards the bottom of the tube. And this is also visible in the concentration profile. In the concentration profile is also visible that we also have almost approximately have a layer thickness of 0.5 millimeters. Then you can also see some results of glass beads of 120 micrometers. So again, you can see here the highest measured flow rate, 1021 milliliters per minute. And you can see that the particles are homogeneously divided. So we have a homogeneous flow regime. And this is also set as standard concentration profile. Then if you further lower the flow rate towards 568 milliliters per minute, then you can see that the particles are starting going to the bottom of the tube, but they are still, they're still divided over the whole tube. So this indicates that we'll have a pseudo-heterogeneous or a heterogeneous flow regime. And then if you further decrease the flow rates, then you can see that we'll have the formation of layers of particles at the bottom of the tube. And again, in the concentration profile, we can see that we have a layer thickness of 0.4 millimeters. Then we will move to the velocity profile. The velocity profile is measured with the same setup as the concentration profile. So it's just the same setup. We will use a centrifugal pump, glass tube, and a high-speed camera. So here you can see two examples of the velocity profile, one at 940 milliliters per minute and one at 384 milliliters per minute. And you can see the pictures with the two flow rates. But let's zoom in first towards the 940 milliliters per minute. You can see two different velocity profile. One velocity profile is of the particle velocity measured with the high-speed camera, and the other is the simulated liquid velocity. We have simulated the velocity of the liquid with software, and then we compared it with each other. And now you can see that there is a difference in speed. So this means that the particles are slower than the liquid. And this is due to a slip force. So due to a slip force, there will be a difference in the particle speed than the liquid. Then if we look to the lowest measured flow rate, then you can see that the particle velocity is higher than the simulated liquid velocity, and that's due to sedimentation. If you have sedimentation, then you will have a smaller geometry of your tubing, and with the same flow rate, you will have a higher linear velocity. And that's the reason why this particle velocity is increased. The simulated liquid velocity doesn't take the smaller geometry into account. Then the influence of the pulsator. The pulsator has a different setup than the concentration profile and the velocity profile. So this setup will use a membrane pump. And why a membrane pump? Because this can handle pressure changes. Then we'll use a PFA tube of 1/8 inch. And then you can see the pulsator inside the setup. There is one important thing with the pulsator. The inlet needs to be at the top and the outlet at the bottom. If you switch those two, then the particles will stay in the pulsator pump head. And that the pump head of the pulsator is, I think, 25 milliliters. And if you don't do it like this, then they will stay inside the pump head. If you do the inlet at the top and the outlet at the bottom, then you'll have the extra gravitational force that will help with the particles come out of the pulsator. And then you can see that we'll use PFA tube of 1/4 inch and again a glass tube to look at the particles with the high-speed camera. So for the experiments with the pulsator, you can see that we have a fixed amplitude of 4.2 milliliters, and we will change the frequency. With each frequency, we will have a maximum velocity, which you can see here on the slide. So let's have a look. So in each experiment, we have measured at 4 different places of the velocity of the pulsator some images. So at 1, it is at the lowest speed, and at 4, it is the maximum speed of the pulsator. And this is a result of 0.34 hertz. So here you can see the 4 different pictures at this setting, and you can see that the particles are still sedimentated at the bottom of the tube. Thus this indicates that this pulsator setting is not high enough to get the sedimentated to the divided towards the whole tube. But then if we further increase the frequency, then you can see at the lowest speed that we'll still have sedimentation of the particles. But if we go to the higher speeds, then you can see that the particles are starting to, to have a homogeneous divided flow regime. And then if we further increase the frequency, then you can see that we have a homogeneous flow regimes in each case. So this is the right setting of the pulsator to get particles in a homogeneous regime. So now we came to my conclusion. First, we have the determination of the solid behavior. So we have done concentration profiles and velocity profiles. So we can conclude that we have a flow regime, that we can detect the flow regimes, we can measure the layer thickness, and we can measure the velocity of the particle. for one suspension, one day. Yeah, a half a day, because you can immediately see it on your recording. So yeah, you just need to put it. Then you need to have a steady state in your reactor, and then you can just measure it, and then you can immediately see if you have sedimentation or not. Yeah, it's easy to, if you can say, okay, with this Reynolds number, you're okay, for example. So yeah, we need to look to the Reynolds numbers or the settings or the Womersley number, which do we need? Yeah, that's the... Yeah, but for the moment, not new. I think it was the oscillatory Reynolds number. Yeah. Yeah. Yeah, for the moment we have just researched one geometry, one diameter, but yeah, we'll look to another diameter as well. But yeah, they are not yet researched, but they are done. I know if you don't use the pulsator with these kind of glass beads or so on, yeah, they will start sedimentate and you will have immediately clogging. And if this happens, then you need to have a safety in your in your setup that your pump will stop or so on. But yeah. I didn't measure it, but yeah, I just... It is nice to know to know which settings of the pulsator do we need. So yeah. Okay, go ahead. Brilliant.
Okay. So my PhD topic is ultrasound-assisted photochemical reactions in Taylor flow. So essentially what we're doing is we're trying to improve photochemical reactions using the effects of ultrasound. But before I go deep into that, why would we want to carry out photochemical reactions, right? So with light, we can access alternative reaction pathways, and we can synthesize complex organic structures. And this can be carried out in 1 or 2 reaction steps, right? So if we look at these 2 examples, right, we can see we can target the specific parts of the organic molecules quite easily, easier than thermochemical and electrochemical methods. This means we use less chemicals and less energy, and we have the ability to perform green chemistry with photochemistry. But of course there are challenges, right? So the first and most important one is the attenuation of light with distance. So if say now you have initial light intensity, the deeper you go inside the reactor, the less intense the light is. And this is described very well by the Lambert-Beer law, right? So you have initial light intensity, and it decreases the deeper you go inside your reactor, and this is even more so if you have a higher concentration of your light-receiving species, your photosensitizer, right? So what does this mean for photochemical reactions? So take, for instance, a zero-order reaction. You see the reaction rate, in most cases, quite a few cases, proportional to the amount of light absorbed. So this, again, we can describe the Lambert-Beer law, and we can equate it to 2 parameters, the received light intensity and the optical path length, right? The optical path length is basically just a different word for how deep is your reactor. So with this equation, we can compare reactors of different sizes. So this is what I've done. So yeah, I compare like a batch reactor, well, a small-scale batch reactor of 0.15 centimeter, and I compare smaller microreactors, smaller reactors, which are typically in the microreactor size range. And if we compare the relative or the average reaction rates of smaller reactors with that of a batch reactor of 0.15 centimeter, we see the reaction rates are much faster, well, the average reaction rate are much faster for these microreactors, right? And this also increases with increasing concentration of your photosensitizer. So this sort of like is the reason for the trend for people trying to carry out these types of reactions in microreactors at the time being. So what does this really mean in terms of production and concentration? So one way to sort of visualize it or to conceptualize it is to divide each reaction layer into a PFR reactor on its own, right? And then you can compare different different systems of these PFRs to compare reactors of different sizes. Right, so if you have the first reaction layer, you have the reaction rate of reaction rate 1, and the second one, third one, and each one decreasing the reaction rate as you go deep into your reactor fluid, right? So say now you have a system of reactors, a deep batch reactor of all 4 layers. You have, and compare it with the reaction where you only have layer 1 and 2. You keep your residence time the same, you keep the initial light intensity the same. You know that you'll have a slightly more production with the setup with all 4 reactors, right? Because you have reactor 3 and 4 producing a slight bit more. But if you compare the average reaction rate of reactor 1 and 2 compared to 1, 2, 3, and 4, the average reaction rate of the second system is much higher, right? Therefore, you will convert more and have less reactant and product in your outlet stream, right? Less to separate at the end of the reaction. And this is what they saw when they are carrying out this photochemical reaction of alpha binary, right? And this is the reason why microreactors in different setups tend to outperform the much bulkier batch and flow counterparts. And the second interesting thing is when they used to introduce a gas phase, right, a second multi-phase flow, Taylor flow in these reactors, they noticed that even if the gas phase is inert, that the conversion tends to be higher for 2-phase than it is for single phase. And this conversion increases the more gas you put in. So a few people, they did a couple of experiments, right, and they noticed, okay, there's no effective mass transfer, right? They doubled the light intensity, double the reaction rate. Also not really effective light scattering. So what you could propose from this is basically what I said on the slide before, that you have different reactions or different sections of the reactor, right? For single phase, you have a film and you have the bulk, right? So the reaction rate in the film is a lot higher than the reaction rate in the bulk. And for 2-phase flow, you have the same thing. You have the reaction rate, you have the film, and you have the bulk, and you have now this big gas bubble occupying some volume. Which part of the volume does the gas bubble occupy? It occupies the volume of the bulk reactor, which is a lower performing reactor. So in overall, your average reaction rate would be higher for the 2-phase case, meaning that you have higher conversion. So this sort of demonstrates the importance of how you distribute your phases in these type of reactors, right? You want to optimize the light intensity by moving your reaction liquid towards the light. It's pretty straightforward. And then the second challenge, well, quite encountered, is mixing and mass transfer. So for quite a few of these photochemical oxidations, that you notice that they tend to work at really high pressures or really low concentration of your starting material. This means that they are most likely limited by mass transfer. This also has led to different reactors, or to overcome these limitations, like the aerosol reactor of Ennis, and also the spinning disk reactors, and they have been performing well. They have even higher selectivity, overcoming mass transfer. So the hypothesis of the thesis, or the project I'm doing, is that the effects of ultrasound in microreactors can not only improve mixing and mass transfer, but also photon transport for these photochemical reactions. This will lead towards higher conversion, increased productivity, improved selectivity, hopefully with mass transfer, and better light utilization and high efficiencies, all while retaining the inherent characteristical safety and versatility of microreactors. So what do we already know about the effects of ultrasound, right? There are two effects that have been reported. The first is cavitation. And these are cavitation bubbles oscillating violently, inducing secondary mixing. This can improve radial mixing and basically mass transfer, as we see in the figure on the right. And the second effect is surface waves of oscillation. So you induce surface waves, capillary waves, on these bubbles. This increases the surface area, which increases then the specific surface area available for mass transfer. So what we are able to do when changing the frequencies is we're able to atomize the liquid into the gas phase. So what we're doing is we're dispersing large amounts of liquid droplets into these gas bubbles with our ultrasonic microreactor. And what we're doing is we're utilizing now this section of unutilized light inside the gas bubble by introducing this liquid volume that was previously not really reactive, and we may be moving it to a more reactive zone. So this way we hope to improve the photochemical reaction rate. And secondly, what you see is also we seem to be breaking up the gas and liquid phases, moving the liquid phase to the liquid form where we already know it's more reactive. And hopefully through these two effects, we can also increase specific surface area and mixing, and overcome not only fast photon transport and mixing in microreactors. So what do we know? Why is this happening for our cases, for our reactors? Is we believe that there's acoustic resonance in the liquid slug, which basically means that the incoming sound waves are interacting with the reflected sound waves, forming pressure nodes inside these reactor channels, right? And we know that particles tend to focus towards these nodes, so that's what we did. We dispersed particles, we applied ultrasound, and we noticed the particles were focusing towards these nodes. So right, we have acoustic resonance, but we can explain why atomization was occurring. So we know from theory that cavitation bubbles above a certain size tend to go to these nodes. So we see them pretty well in the center of the channel of the slug, but we didn't know if they went at the interface. And that's what we eventually did using high-speed footage and a lot of light. We managed to see cavitation bubbles oscillating at the interface, breaking up these gas liquid slugs. So what this basically means in terms of performance is we can try and control the aerosol or the droplet sizes, the amount in terms of frequency that we apply, right? Because you change the size of the cavitation bubbles. And that's the aim. To first carry out some axonometry to try and characterize this reactor in terms of photon transport. And once we've done that, we'll carry out a few reactions to prove the concept. Thank you. Yeah. Oh, well, it was purely accidental. I was doing a mass transfer study, and I just increased the frequency, and there it was. It's more to do with the piezo itself, right? So anything between 300 and 700 kilohertz, you'll probably atomize your thing, but it depends on your reactor. Okay, what is it designed to operate at, right? So yeah, you design your reactor, you know what frequency operates, you do the reaction, right? So Yeah. Hotspots, okay, that occurs. We're trying to check that out. Hopefully temperature control is pretty good in microreactors, so we hope that would be good. And the formation of radicals. So the first test we always do before carrying out any reaction is just in the dark, right, to see if radicals do actually do something to organics. But yeah, compared to, because you have some methodologies to form radicals and you know that it's light and things like that, and you can actually measure how much cavitation you have. But this time range is usually hours, right? You have to operate for hours to produce enough radicals to do this. And I'm talking about 1 or 2 minutes residence time. So the amount of radicals we're producing is quite small, but it would be nice if because you could also use that to convert your compound, but it's also not necessarily the case. Yeah, sure. How I came here, yeah. Ennis is my co-supervisor. Yeah, Ennis is my co-supervisor, so he suggested I come together with Simon Kuhn from Co11. In 11. Yeah, thank you. Yeah. Ennis has been very friendly and very helpful with what's available. Yeah. Also, Emine, yeah, she's been helpful a lot as well. With respect to chemistry, she works on something very similar. Yeah. So, yeah, so actinometry, like this reaction should be able to give me, it should be able to tell me how much light I'm giving to the reaction, right? And this won't change, right? If I change different reaction chemistry, this would be. And the optical path length, which is the second parameter we're going to determine from it, this is inherent to the reactor. So if we know that if we keep the photosensitizer concentration the same, we know how much light we're giving to that, and hopefully we can isolate then the photon transport from the mass transfer. So the idea is to do 2 different experiments, right? One where we just measure photon transport, one where we measure mass transport. We know a rough idea of KLA, the absorbed amount of photons for these certain conditions. Then we can say, maybe this would be our limiting step, right? So what would be our limiting step in the first case, and see. Yeah. Oh, what's nice about these reactors, like you have a nice selected Taylor flow, and you can look at the top of them. So if you have like a liquid gas slug, you know what its size is, right? So you can see its size literally shrinking as it goes through the reactor, and you can measure, the difference in the size from the start and the inlet and outlet, and you can say, this is my mass transfer coefficient. That's one way, but with ultrasound things get a bit crazy, right? So what we're doing is we're adding a dye that reacts with the dissolved carbon dioxide or dissolved oxygen, and you can measure the concentration of the dye and relate that to amount of gas that has been dissolved inside the reaction. That's sort of like the idea I think is most likely to work. Thank you.
Okay, good afternoon. I am Matthias Jacobs, and I'm going to tell something about the translucent monolith, which can be used to scale up photochemical reactions. So, why is photochemistry good? So, there are many advantages, such as it is less energy intensive compared to other reactions. It is highly selective, and you don't need or need a low amount of hazardous solvents. And as an additional benefit, you can access different pathways which cannot be accessed with normal thermochemical reactions. It has a high potential, but it's not often used in the industry, and this is due to the limited scalability of photochemical reactions in the standard reactors, such as the batch and the microreactor. So this is on the left-hand side, you can see the batch reactor, and on the right-hand side, you can see a graph which I've drawn, and this is based on Beer's law. As you can see on the x-axis, this is the path length, and on the y-axis, the intensity, that after only 0.4 millimeter, all the light is absorbed. And this is what you also can see here in the batch reactor. Over-irradiation at the top, and no or low illumination at the bottom. So this is not scalable, since if you increase the path length, the light wouldn't reach down to the bottom. And since this also has a low surface area to volume ratio, you can have mass transfer limitations when you're using multiple phases. So let's go to the microreactor. The microreactor does not have these issues. It is a small channel, so 1 millimeter or less, so you absorb less light. Well, you don't have under irradiation. And you have a high surface to volume ratio, so you don't have these limitations. However, you have a low throughput or productivity, and you need to have a high productivity in the industry, since you need to make product which you can sell. And since you have a small channel, as you can see here, a lot of the light is just wasted, so lowering the energy efficiency. What if we put these microreactors next to each other and beneath each other? Then you get this kind of monolithic structure with the same advantages as the microreactor, but with also the benefit of high throughput and also higher energy efficiency. But it's not used in the industry. It has been investigated previously, but there were some issues with this design. So the first thing is it's opaque, so a lot of light is lost on the reactor walls. And you see these optical fibers here to introduce the light. These cables or fibers are designed to keep the light inside, so you don't irradiate your reaction mixture. And furthermore, you introduce a fiber, so this reduces your useful volume. And that's why this reactor design was suboptimal. The solution to this is to make this whole system translucent, so you don't lose light on the walls, since they are translucent or transparent, and you don't need these optical fibers, since you can just irradiate from top or any other side. So this is what I'm going to talk about, how to design the translucent monoliths, and in the end, I will compare them to the other photochemical reactors. How do you design the monolith? And what is the optimal channel configuration of the monolith? So here you can see your monolith. You can vary the diameter of your channels. You can vary the horizontal offset between the rows. So that means this row to the right and this stationary or any other configuration. And you can also vary the vertical offset. And I'm going to discuss now which one you need. So for the diameter, a small diameter means that you have a large surface to volume ratio. You have the ability to perform different flow patterns in the reactor. However, it is a small channel, so you have a low throughput, and it's more difficult to construct these channels. So that's the disadvantages for it. You can also choose for a large diameter, so you have a large throughput. It's easier to construct, but you have the over and under irradiation, as I just mentioned. In this research, I chose the smallest diameter which I could possibly fabricate, which is 1 millimeter. The reactor is 3D printed, so that's why it's because 1 millimeter is the smallest. So what about the horizontal offset of the rows? So when there is no or small horizontal offset, you get this over irradiation in the upper channels and under irradiation in the lower channels. And as an additional benefit, some light is not used between the channels, so you don't want to have this. However, if your offset is too large, you have less or no over irradiation, which is quite nice. But again, most of the light is not used between the channels. And in a few minutes, I'm going to show you what you need to solve this issue. And for the vertical offset, the hypothesis is that there will be not much of an impact on the power absorbed in the channels. How did I determine the parameters? So the optimal parameters, I used COMSOL with a ray tracing algorithm to determine the optimal configuration. I varied the horizontal distance between the channels, or the rows, between 0 and 3 millimeter. The vertical distance was also varied between 0 and 6 millimeter. And then I calculated the amount of light absorbed in these channels. And here you can see the geometrical domain of the COMSOL model. You have an inlet, then the light goes out to the detector, and this is your sample here. And in these channels, the light is absorbed. This is the graph which combined all data. So on the x-axis, you can find the horizontal offset, y-axis, the vertical distance between the channels, and the colors mean how much power is absorbed. Yellow means a lot of power absorbed, while blue is low amount of power absorbed. And you don't want blue, but you want yellow. Let's start with 0 offset. This is shown here. There is a large space between the channels, so the light will just go through it, so not a lot of light absorbed. When you go to 1 millimeter of offset, you see that more light is absorbed, which is what we want. And when you further increase the offset, you go back to scenario 0 or 1, which is here, and then you have a low power absorption. The graph here is symmetrical since you just shifting the offset. This is for the horizontal offset. Now for the vertical offset, then we just follow one line here. Let's say the 0. You see the colors don't really vary, so there is not really an impact of the vertical distance. And so the conclusion of this graph is you have a low impact of the vertical distance, and to have a good absorption or the largest absorption, the horizontal offset should be equal to the channel size so that you absorb the most light. Now the comparison of translucent monoliths with other reactors. Here you can see my setup. Here you have the LED board, which is water cooled, and also the monolith itself. I'm going to use two benchmarks to assess the productivity and the energy efficiency. The first one is space-time yield, which is the amount of product you form per reactor volume and per time. Ideally, you form a lot of product in a small reactor in the shortest amount of time possible. And the PSTY is some kind of energy measurement, and no, energy efficiency measurement, and it is the space-time yield divided by the divided by the power of your lamp here and the volume of your reactor. So these two are used. Then we need to select a reaction, and in my case, it is the photooxidation of DPA with singlet oxygen. Why, you may ask? It is often used in the literature. Only one reaction product. Remember the first slide, which I say it is highly selective. This is what you see here. And the product is also easy to analyze with HPLC. And here I also varied some monoliths. So this is the standard monolith. You have 16 channels per row, 2 rows. Monolith 2 is a variation of monolith 1. It's doubled in width. Monolith 3, it's doubled in channel size. And monolith 4, it's doubled in depth. And here you can see all the data of the comparisons. So first you have different reactor designs here. Remember, space-time yield, productivity, PSTY is energy efficiency. This is the batch reactor. As you can see, it has a low space-time yield since you have a large amount of dark zones, and a high PSTY since you have a large volume that absorbs all the light. But what's good of a reactor when you produce a small amount, but it's highly energy efficient? You don't want it. So this is the fluorescent fluid photochemical microreactor, FFPM. It has a low space-time yield, since it has a low throughput, and also a low PSTY. Since a lot of light is wasted here, the light source is not really optimal. So that's why it has a low space-time yield and also a low photochemical space-time yield. The next design is somewhat similar. Also low space-time yield due to the low throughput. It's a little bit higher since the light source is better designed on the reactor itself, but still a low PSTY since you lose a lot of light to the surroundings. They just go through the reactor without reacting. And then you have the monoliths. Monolith 1, 2, and 3. Here is again the setup. So it has a high space-time yield and also a high photochemical space-time yield since the majority of the light is used. And here you can see again what the variation was between these monoliths. As you can see, all the monoliths outperform the other reactors except the batch reactor, but it doesn't produce a lot of product, so you don't want that. So the reason, so I'm going to explain why these monoliths have some differences in space-time yield and photochemical space-time yield. First thing is, why does these monoliths are better than the rest, since the light source is also optimized to the size of the reactor. If the light source is too small, only a part of your reactor is illuminated, so you don't get fully irradiation in your reactor, so not everything is converted. If your light source is too big, then you fully irradiate your reactor, but you also waste a lot of light to the environment or your surroundings. But why has monolith 2 a higher PSTY than monolith 1, since it's only doubled in size? This is probably due to edge effects. So let's give a certain number to these LEDs, 10 watts here, 10 watts here. You lose 5% to the left, 5% to the right, and then you lose 25% to your surroundings. For your monolith 2, you need more LEDs, double of course, otherwise it's not fully irradiated. So again, here you lose 5 watt, and then you have a lower amount of light wasted. So the conclusion is, for the design of your monolith, you want to have a small channel diameter for the microchannel characteristics. The vertical distance between the channels doesn't make a difference, and you have a large impact of the horizontal offset. So the channels should slightly overlap, and the monoliths have a high space-time yield and photochemical space-time yield compared to other reactor designs. Because the light source is optimized to the size of the reactor, and you have less over and under irradiation compared to batch reactors. And that's it. Here's again a photo of the translucent monolith, which is used in the reactions. Okay. Looks like everything was clear, or yeah, this is almost top down. It is slightly angled. Yes, they are. It is certain interesting to add a third row of channels, but you need to optimize the concentration of the photosensitizer. Otherwise, the upper channels absorb all the light and no light will reach the bottom. So when you lower the concentration of the photosensitizer, you absorb less light in the top layers and more goes to the lower layers. To optimize it, well, you can just do some experiments, I guess. So you don't need to use the almighty AI to optimize everything. So. Well, it depends if there is funding for research, I would say. But that's certainly an option, I think. Yeah. But you see, I think there is some potential since he's using solid-liquid reactions, and there are many solid-liquid reactions in photochemistry with titanium dioxide. So I think if we can combine our work and have a steady stream of particles and fluid, and you can evenly irradiate them, it would be a nice combination, I think. Yes? Okay, so I made it with stereolithography. This one is made with a Form 2, but right now I'm outsourcing this to 3D systems in which they also use the SLA, but you can print bigger designs. So if that's okay. Yeah, that's a quite interesting thing you said there. So the flow distribution, so when you're distributing the flow over different channels, it's a common problem, which you often see in the literature, is that you get a certain maldistribution when you try to and this means that you have more fluid on in certain channels than the others, and you don't want this, of course. So we try to minimize this maldistribution by using a symmetrical design with this distributor. So in literature, you see that the maldistribution is, depending on the distributor, less than 10%. So which is within range, I would assume. Yeah. Does this answer your question, or? Mm-hmm. Yeah, so it does have an impact, especially when you're using multiple phases with slug flow. So when you do it horizontally, the slug flow, it's not that great, since air will go to the top, water will go down, so the maldistribution is quite high. So you really need to find the optimal, not configuration but position of your monolith. So right now I'm using this in the upwards position. Flow goes from top to bottom, so you mitigate most of these gravitational effects. Liquid and gas both from top to bottom. If you do it otherwise, the other way around, it doesn't work. It's mathematically proven that it's not working in monoliths when you do it from bottom to top. Kiran or Leen? Yes. It is a problem, and so you try to reduce the reflection of the light, since all light that is reflected is money wasted. So you try to reduce this. So you want to have a 90-degree angle, so you lose less light. Otherwise, if there is a slight angle, you lose more light. And this is something you need to make sure of in your experiments, Since if there is an angle, there is less light than you expect in the reactor, so the reaction rate will be lower, and then you can make the wrong conclusions, I think. I do, so, well, not for this material, since I don't know exactly the refractive index, since it's based on reflective index, but I would say 4% that is reflected back to the top. Kiran? Mm-hmm, mm-hmm. Yeah, so the reason why I picked this design is that I know it has a larger footprint, as they said, but I tried it with the manifolds, and that's also at the end, but it didn't work out. The distribution was much higher when I used manifolds compared to the distributor, this type of distributor. Yeah. Well, that's a question which can be, it is difficult to answer that with numbers, since it depends on so many variables, like the photosensitizer concentration, since if you have a large concentration of photosensitizer, no light is absorbed, but you don't want that. I was planning to measure this, but what you can do is just put a mirror behind the reactor, and then probably that's where you were going. Mm-hmm. 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 Yeah, so actually you can increase your conversion with that. So, and the funny thing is, when you lower the concentration of the photosensitizer, you would expect a lower conversion since you absorb less light. But when you put a mirror behind it, the upper channels get less light and the lower channels get a little bit more light. The light is reflected back to the lower channels, so it's almost equally irradiated, and then you will increase the conversion. Yes? No, I did not do that yet. That was on the planning to do that. Mm-hmm. 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 Which is part of the plan to do in the coming months. Mm-hmm. So you mean a partial recycle? Ah, I see. That's also possible if you put a valve on it, and it's. Yeah, I'm definitely going to do that. But if I'm not mistaken, you also need to have the reaction rate or the reaction order to calculate it. But the issue with this photochemical reaction is that sometimes it behaves depending on the concentration of your photosensitizer. Sometimes it behaves as a zeroth order reaction, and sometimes it does as a pseudo first order reaction. So yeah, I can do that, but then I need to, well, it's not too much work, I think, to do both cases. But I think it's a great idea to first. Yeah. No, I did not yet. Well, perhaps I'm limited by mixing, so that's why I'm going to perform some experiments with slug flow, which will introduce the mixing. So that would be quite interesting to see the results.
Good afternoon. Okay. Yeah. Okay. Good afternoon, everyone. Today I will give a presentation about the modeling a complex reaction process from Raman's vector data. And here shows the outline of today's presentation. Firstly, I will give the short introduction about this research, and then is the specific process, how to model the process, and then the methods applied to model this process. The last two parts will be the results and conclusions. As we know, the AI is now a very popular topic. It can do better things than humans sometimes, and the AI revolution in chemical engineering has only barely begun. It's based on someone's research, and also thanks to the computational abilities and the software environment, we can see the opportunities in AI engineering has increased a lot. And the AI applications in chemical engineering can date back to the 1980s. And at the end, you can see the two examples and successful application about the AI in chemical engineering. One is the product prediction in the organic reactions. Another one is about the surrogate modeling of the fugacity coefficient. And my research is mainly based on the reaction process. We all know how its reaction looks like. And here the block diagram shows the typical process of the chemical plant. After the raw material storage, the feed preparation, then this is where reaction happens, and after that will be the separation purification part. So it is so important because this is where the product forms, and if we do a great job here, the separation and purification will have an easy job. And we have a huge potential to get improvements by changing the reactor conditions and to minimize or to solve the difficulties of the maximizing the desired reactions. And also we need to consider about the trade-off of the reactivities and byproducts of different reactions in several one reactors. If the reactors the reaction process is a telescope process, we also need to think about the selection of the multi-role reagents. And next part is about the process, specific process about my research. Here we consider about two processes. I will introduce later about simple bench process and the continuous flow process. And what about the reactions happens in this process? In my research, I consider about 6 reactions. One is the main reaction to A plus B to go to C, and important side reaction B plus C to go to D. And the reaction rate is based on the power law, as we see in the table. And the other 4 is the unimportant reversible reactions. And the reaction rate for different components is based on the equation of here, and the reaction rate constant as well as the reaction heat is calculated by the Ayres equations and the forward addition energy and the backboard addition energy. The next part will be the process I said before about the single batch ones of reactors. And here we can see we put one component B in the vessel and then feed another component A, and based on that we use the Raman analyzer to get this measured signal, and based on this signal we can get the information we want, like the concentrations. And to model these single batch reactors, we use the equations listed in the left and about the concentrations of component A and I, and the concentrations of the other components. Also the volume changes and mass changes is also listed here. Another part is about the heat. The accumulated heat in this vessel is calculated by the heat in and the heat out. The accumulated heat is also based on this mass and specific heat capacity, and the heat in involve the stirred heat the reaction heat and dosage heat, and heat out is the jacket flow takeoff. And then about the continuous flow reactor. This continuous flow reactor have these 3 reactors in series, and for each reactor they have the separate jacket temperatures. And for one reactor, how I model that is use this CSTR in series. And for one continuous flow reactor, divide into 10 flow CSTRs, and for one element it is a CSTR as shown in this diagram. And for each element of this CSTR, the mass balance, energy balance are all listed in the right side of the slides. Yeah, it's about the methods. So to model this process, here I used the structure as listed here. Firstly, we got the data from the experimental, and the data, of course, have the input and output. In my model, I use the input as the initial concentration, mass and volume, and feed concentration, flow rate, and temperatures. And the output is concentrations from the Raman spectra, which is converted from the Raman data in the weight mass. And another one is the heat generated by the reactors in watts. And based on the similar reactions from the literature, we can have the constraints for the parameters we will estimate. And the parameters involved about the whole reaction system is like 22 kinetic and heat parameters, including the addition energies and the heat of the reactions. The methodologies here to estimate these parameters are the swarm intelligence algorithms. In this research, I involved the slime mode algorithm SMA and cloning optimization ACO and the particle swarm optimization PSO. And talk about the data, because as we know, the data is from the Raman spectra, but how can we get that data from the Raman spectra? Firstly, we need to calculate the area as a select peak position. For example, for component 1 or component A, it is at the Raman shift 1600, and then for that peak we calculate the area, and from the literature study we know these areas after the nomination it can have a direct connect to these concentrations. So then we developed a small model to predict these concentrations from these peak areas. And about the objective functions in this diagram here, what I use here is this normalized mean squared error, and the error is the total number of the outputs, and NK is the total number of these data points we involved. And the R1 is this regulation term. Here we used here is to avoid this oscillating of the parameters in case for same results we have a different set of the parameters. And the final objective value is the sum of this normalized mean squared error and L1 term. About this swarm intelligence, so the swarm intelligence is a subset of the optimization methods. As we know, these conventional methods is based on the mathematical iteration, including the linear programming, non-linear programming, and the dynamic programming. And for the non-convolutional methods, it can divide into the swarm intelligence and the involutional algorithms. The involutional algorithms includes the differential evolution, and for the swarm intelligence, for the different categories is based on the animal, insects, bacteria, or other. The others, the FWA is for the fireworks algorithm. And in this research, we more focused on the PSO, ACO, and the SMA. Here shows the details about the slime mode algorithm. It is based on the food approaching methods by the slime mode. We start from the finding the food, and then approaching the food, then adaptive changes, and then wiping the food. These processes are represented by the mathematical equations, so we can use the similar approach like the slime mode to get the food and to get the final point, the final parameter or final point what we want. And another algorithm is about the ant colony optimization, and it is based on the food approaching by the ant colony. And this algorithm is initially for the discrete optimization, but after the developing and updating, it now can used for the continuous domain. And between the nest and the food, they can find the shortest routes to get their food back to their nest. In that way, we can get this best solution, the best set of parameters in our case. And another one is the particle swarm optimization. This is based on the bird swarm behavior. And the main difference between the particle swarm optimization and the ACO and the SMA is that in the PSO, we only have several points, and this number of the several points is fixed, and the update of these points is based on the information from the other points, and at the end we get the best particle of the swarm. But for the ACO and SMA, every iteration will generate new points and replace the bad ones, so it is takes more time to calculate. And then is the results. So first results is to get the peak area data from the spectral data, and for that we have done some mixing experiments, and the figures here shows the accumulate shape of these different spectra, and for from one compensation 0 to the another compensation 40%, all these shapes are showed here, and the same is for the B component. And so the corresponding areas can calculate based on the methods I mentioned before. And because of time difference of the device and experiment done, a large amount of data is near the boundaries, and the experiment 1, 2, 3, 4 are all marked where is this experiment done. And the concentrations of A and B ranges is already covered the ranges of the later experiment for the single bench experiment and the continuous flow experiment. So then is the results from the peak areas to the concentration. So we have the normalized peak areas, and then we want to connect these normalized peak areas to this concentration in weight mass percentage. And this prediction model shows a very good prediction, and these numbers of the data showed here is only the testing set. It not includes the training set, and the number here is like 1/3 of these total numbers. And the method used here is a polynomial regression with the 2 degrees. And then we plot these arrows based on this prediction, and we found the most relative arrows is within the 5%, and the high arrows is near the boundaries. So when we use the data, we should keep in mind that the arrows is there. And then we use the same algorithm, the same model here to convert the single bench data. And the dashed line here is the converted values, and the field bar is the arrow ranges, and the component C is from the A and B, and as well as this later assay report. So component C did not have the direct experiment data, but need to guess. here shows the training process of different algorithms of the convert data. And the shadow here is the history of 10 rounds. And in each diagram, you can see the average ones, the best one, and the worst one. So the ACO, we can see that can achieve the lower cost at the beginning. So we recommend if the computational power and iterations are limited for some cases, the ACO can be employed. And the SMA achieved the lowest cost at the end. After 800 and 600 and 400 for the SMA, ACO, and the PSO, there's no significant improvements. So we can find that the SMA have the potential to fine-tuning all these arrows to go to the lowest, but for the PSO after the 400, the more iterations, there is no meaning for more iterations here. And also the deviations for the different rounds for the PSO are the highest, and for the SMA is the lowest. Based on this diagram, we can see that SMA performs the best among these three algorithms. And then is the use these parameters we got from the swarm intelligence algorithms. And firstly, I would like to discuss the location of these parameters. So this ACO can get the parameters very close to the boundaries. And this is not what we expect, because it can lead to the non-physical meaning parameters. But for the SMA, it shows the better performance compared to the PSO and ACO, because the PSO also showed a lot of different parameters. That is also what we don't want. It is too much difference, and the stability of this algorithm cannot guarantee in our case. And so based on that one, we can see that this SMA shows the better performance. And then use these parameters get, we applied that to the RC1 model, which is the reaction calorimeter model, and to get this QR, the reaction heat. And the experimental data and the model data are very close, and the R-square determination coefficient can go to 0.97. And a similar application to the single bench model with these SI results, and this determination coefficient can all go over 90% of the overall. Then we use the same parameters from the single bench reactors to the continuous flow reactor. And here shows the modeled concentration in the reactors after a certain time. And the A and B concentrations are as expected. And also at the bottom of the left, you can see the model temperatures inside the reactor after a certain time. The last diagram is try to compare the experimental data and the model data. And we can see that model data can, the modeled temperature can catch these experimental data tendencies very well. Then about the concentration, about the conclusions and the future work. We can make a conclusion that this SMA outperforms the ACO and PSO with the proposed structure, and the proposed modeling with the SI algorithms gives the promising results when we applied it to the plant scale reactors. And the future work will have more research on this Raman spectrum. I would like to get more reliable information from one single Raman spectrum. And now this diagram shows the current model with the experiment model, and the specific peak positions calculated from the geometry of these molars of different chemical species. And that's all about my presentation. And thank you for your attention. If you have any questions, I'm open now. And yes, these all letters are the chemical species in the solution, but we can only measure the A and B. So at the end, what we can compare to the experimental data is the A and B. So that is why I said the A and B concentration as expected, but the other components cannot measure in the conclusion. Yeah, the solution. Yeah, and yeah. In fact, this line mode algorithm haven't applied in the chemical engineering yet because it is a relative new algorithm start from the 2020, and for the PSO and ACO, it is have developed a lot over several years, maybe 10 or 20 years, and they have applied in chemical engineering for certain years, and especially in this parameter estimation. Any more questions? Okay. Then we can have a break. Oh, yeah, sorry.
Have you ever asked yourself why a football is round? Probably not, because it seems so obvious. A football is round because it should be able to roll over the field. Exactly. And this easy constatation is the key for a much more efficient production process in the pharmaceutical industry. In the crystallization step, solid particles are formed, and if these solid particles were round, like the football, they would also be able to flow or to roll or easily flow between the different processing steps. But none of the pharmaceutical components crystallize into round shape naturally. Some even crystallize into a needle-like shape, which results in a very poor flowability. Therefore, in my research, I will investigate spherical agglomeration. This is a crystallization technique in which an extra solvent, the bridging liquid, is added to create, to bind or connect the existing particles and to create larger and much rounder agglomerates. In the first work package, I want to do some reference experiments in batch reactors to acquire knowledge. Secondly, I want to correlate the particle properties with flowability to make inline measurements possible. And in my third work package, I want to optimize the dropwise addition of bridging liquid by the droplet size, the amount of bridging liquid, and the pulsation settings. Lastly, I want to combine the nucleation and the agglomeration growth step in a continuous flow reactor and a multi-stage CSTR. So hopefully next time you watch a football game, see the ball rolling over the field, you will think about my continuous spherical agglomeration and how it will result in a much more efficient production process in the pharmaceutical industry. Thank you. Yes. No. So the particles are formed as small particles of around 5 to 10 microns, and then they are agglomerated into larger particles, as I said, but they stay in this larger form because larger particles also have a better flowability, as they are also easily flowing through the process, and they also do better infiltrations, etc. And for the and because they're round, they're also they're having also a better flowability, and so they stay in this agglomerated form. Yes. No. So yes, indeed. So they sometimes they're tableted, so they're compacted in a tablet, and then the larger particles are also better because they flow easier in this tablet form. Yes? Yes. So I need also the bridging liquid and the pulsation, because when I only apply the bridging liquid, then without the pulsation, then the bridged liquid wouldn't find the particles to agglomerate, and by the pulsation there would be more collisions between them to make them larger and more compacted. And also the bridging, and if I only use the pulsation and no bridging liquid, then the particles wouldn't be this round. So agglomeration happens a lot in the pharmaceutical for pharmaceutical components, but then they are not they have not as nice round shape, which results in again a bad flowability, as I said, and due to the droplets of the bridging liquid, they more or less take this round shape of the droplets. Yeah, so in a first system I want to use is benzoic acid, and here I want to use water and ethanol as the anti-solvent in the solvent, and toluene as bridging liquid. Yes, indeed. Yeah, okay, but yes, but what I meant to, what I said to him was that the particles stay together, but the droplet, the bridging liquid is more or less squeezed out during the compaction phase. So when the particles, the agglomerates raise, and then they are compacted with due to collisions and other and the penetration of other solids inside the bridging liquid, but then also the bridging liquid is squeezed out from the agglomerates. Of course, there will be some bridging liquid inside the agglomerates, but it was already studied that the drying step, which is also coming after the crystallization, almost removes everything. Yes, because the bridging liquid is chosen. It actually has two. So the bridging liquid has to be immiscible with the solvents, which is. But it has also a higher affinity for the solids than the solvent around, and therefore they are really going inside the bridging liquid droplets. Yes. Um, Inside the bridging liquid, they will bound. Form bonds with the other particles, but they will not grow anymore because there is no anti-solvent solvent available anymore. Yes, they don't dissolve in the bridging liquid. Yes. Yes. Yes, indeed. So that's something I really want to study in my third work package. So I want to make a residence time reactor in which I can place a high-speed camera, so I can change the droplet sizes and the amount of bridging liquids to the solvent to avoid at all time the slug flows, and to see which droplet size would be the best to catch all of the solids at the end of the reactor. And I want to change the diameter of the capillary at which I want to add the droplet size to change the droplet sizes. I'm sorry? Mm-hmm. Yeah, that's something I have to look further in detail if I start working on the work package. But thank you for the information. Yes? Yes? Mm-hmm. I have no idea yet, but the particles are really going inside the droplets. So, I don't know if it makes a difference, but I have no idea how it will change the surface area, surface tension. Yes, yes. Yes. So I want to have big crystals, but the crystals are still between the 200 and 500 microns. And to avoid fouling, you need a diameter of your tubing which is 10 times larger. So it's a rule of thumb, and I'm always carrying for this rule. And also the pulsation will prevent from fouling because because of the shear forces which are created. Yes. Yeah, so it is already studied, but it's only studied in batch reactors. And so if we want to, the interest is raising in the industry to go to continuous systems, and therefore, so it is already studied, but just not in a continuous reactor, because it's also new research over the recent years. So therefore, it was not already applied in continuous systems, but. Yes, there would be a large difference, but therefore I want this pulsation, because in a batch reactor you have the agitation of the stir, and therefore I want to apply the pulsation to have the same collisions between the particles. But also we did a lot of research in continuous crystallization in CIPT, so therefore there is also a lot of knowledge to make it possible, yes. Okay. So it is also applicable for for two questions, isn't it? Okay. Yeah. So it's applicable in more industries than only the pharmaceutical industry. It's just in the industry where solids are formed and where the flowability is very important. It is a technique. Is a good technique to apply, and it's so it's useful in for more components, more systems. Yes. And the second. I have no idea yet. Okay.
Als we het eens testen, gaat het wel werken.
Hallo?
Ja, voilà, dat is groot. Ik kan deze gebruiken. Dat is wel geen idee.
Moet je nog een beetje in het groot zetten. Oké. Photoelectrochemical cells with the right photocatalyst can be a solution to convert carbon dioxide and sunlight into fuel. However, these cells show low efficiencies and are way too expensive. This is caused by mass, electron, and photon transfer limitations happening at several places in the cell. So, focusing only on improving the photocatalyst, like most researchers, is not enough. I'm going to redesign the whole cell structure and create cells that have a high surface area and will rely on convective mass transport. These cells will then form building blocks to be replicated indefinitely to provide photochemical processing units that will cost less than $100 per square meters and will have a solar to fuel efficiency of at least 2%. How I'm going to do this? Well, I'm going to use thin catalyst coatings. In this way, molecules and electrons don't have to travel long distances. I'm going to put these coatings into repetitive structures. This will increase light harvesting. Then I'm going to 3D print the electrode structures into complex geometries with aluminum doped and undoped zinc oxide, which is transparent and electric conductive. My team has proven in a previous study that this reactor design has the best light efficiencies of any immobilized catalyst reactor. With this cell, we will create an opportunity to close a carbon cycle and efficiently store solar energy. When I did my master thesis in Portugal, I became passionate about solving the environmental crisis. Additionally, I will conduct this research together with a team which has a lot of experience in photo flow chemistry. Thank you for your attention. I said $100 per square meter because current systems are currently, with that solar to fuel efficiency, too expensive to be viable. It's more than $100, I don't know it specifically, but it has to be $100 to be viable with that percentage. The goal is really to eliminate the transfer limitations, and then we hope to get more than 2%. So it's not my main focus. I don't know yet. I have to investigate this. I didn't look into it, but I will look into it in the future, and yeah, it's very, yes, for sure. Yes. It's yeah, it's I chose methanol. I chose methanol because my focus is not really what type of molecule I'm going to create, but I chose methanol because it's high energy density and it's very interesting for the industry. But indeed, maybe for future work, we can change other, yes. No, I don't know. I know that Matthias also is focusing on thin coatings, but I know that thin coatings is necessary because these coatings will decrease transfer limitations because electrons have difficulties to reach the surface because it's too long distances to diffuse. Also, molecules have to diffuse long distances, so we know that by using thin coatings, they don't need to travel the whole pathway. They just really can react. Well, all researchers focusing on the photocatalyst and using thick coatings to increase light harvesting. But the problem is light can only penetrate more than 5 micrometers, but molecules can't penetrate that distance. So my innovation is using thin coatings and then putting them in a repetitive structure to increase light harvesting, so the light is still be used. Oh. Because with photovoltaic, you mean like the solar market, for example? Yes. Yes. The problem is they have some issues with storage. So they absorb a lot of light, they turn a lot of sunlight into energy, but they have batteries have storage issues. So we will create a cell that maybe can solve that storage issues. Yeah, because that focuses more on the efficiencies and improving efficiencies, but my focus is more on showing how you can decrease transfer limitations. Yes. Yeah, the first question, we know by playing maybe with the pH, we can turn the carbon dioxide into hydrocarbons, and so we can maybe improve the efficiency. And also for the second question was about, yeah, the second question was about catalyst coating. We know that first we will use copper oxide on our cathodes, and we know that it has a very good selectivity for methanol production. Yeah, we can use maybe then in the future other catalyst coatings, but when we have proven that we can eliminate mass transfer limitations by using thin catalyst, we can then use it for other catalysts and complete our photoelectrochemical cell. Yeah, okay, yeah, indeed, I will use this information for sure. Shoot. Okay.
Hello, can you hear me? Can you hear me? Can you hear me? Very good. So, good morning, everyone. My name is Ulderico DiCaprio, and today I will go through the hybrid modeling of a batch separation process. Here we have of the agenda of today's work. So we'll go through the introduction about the aim of the work and the solvent switch case, the methodology, and the results. As we know, the model is the crucial element to optimize a process. This is something that also we experience during our daily life. Nowadays, AI are coming to our daily life, and we all know how we get mad when Google Maps choose the wrong street and it stuck in the traffic, or when it drives us to a closed street. What we will say are not nice words to Google Maps. So it's really important to have an updated model. To update a model, and we have also did this problem in chemical engineering, because imagine that you are optimizing a process and then suddenly the process changes and your model is not able to follow the behavior of the process anymore. A solution to this could be the usage of the hybrid modeling, as showed here in the slide. The hybrid modeling are a quite new technology to model process chemical processes. As you can see, they are built by a first principle part where we will have all the equations that we have learned during the university year, for example, BLE, mass balance, and energy balance, heat transfer coefficient, and so on. And then we have the eta-driven model. That is a statistical model built on the data of a process. As example of this, I will use the solvent switch process. The solvent switch process is a special process from pharmaceutical industry, and it is needed to switch the solvent from the crystallization solvent to the from the reaction solvent to the crystallization solvent. This is done by using a two-step approach. At the beginning, the volume of the solvent reaches a minimum level that is equal to the solubility of the API. And then we have the evaporation of the crystallization solvent while the solvent blend is evaporating. As you can understand, during the evaporation, several phenomena can happen. For example, the unexpected crystallization of the API. We can have the homing effect or the failure of one of the components. In the case in analysis, we will need we will investigate a solvent switch that employs the switch from dichloromethyl to acetone. Let's go to the methodology. Here in the slide, I have reported the data. This works. Okay. Here in the slide, I have reported the data I have used for this study. As we can see, we have that the the crystallization solvent is stored in a feed tank, and then we have the information about this feed tank, basically the mass. Then we have information about the heating speed and the temperature of the liquid inside the reboiler. This temperature has an error of plus or minus 5%. Then we have the volume of the liquid inside the reboiler, but we cannot rely too much on this variable because, as I have said, unexpected phenomena can happen, and then we have also an effect of the steering speed because as you know, if we steer too fast, the upper surface can bend. Then we have the temperature of the service fluid inside the jacket that is needed, of course, to supply heat to the system. Then we have the reflux direction here in number 6. In this case, the solvent amount can be routed either to a receiver tank or back to a reboiler. Then we have the refractive index after the condenser in number 7 that is used by the operator to investigate if the solvent switch is completed or not, because is a track of the relative presence of the two solvents. And then we have the volume of the liquid inside the receiver tank. That is the volume of the evaporated amount. This is by principle because on this line there are some loss related to the vent gas and the pressure regulation inside the system. The data we will use are coming from a partner company, of course. Here in the slide, we have the more or less the modeling approach that I have used. The system is composed by 13 differential algebraic equations that represent the white box model, and in these 13 differential algebraic equations are included mass transfer, mass balance, heat transfer, and vapor-liquid equilibrium. Then for the heat transfer, I have used the Nusselt correlation reported here in the slide. About this Nusselt correlation, we know from literature that this value k is a value that is independent by the all process variable. However, in this case, experimental evidence have seen that this k could be impacted by the volume of the liquid inside the reboiler. Of course, this is not true, but in this case, we are loading all our unknown about the behavior inside the mixing during the mixing. Then we have the enthalpy we have a second deviation that is the enthalpy of the liquid. This enthalpy of the liquid deviates from the ideal condition because we are modeling by using thermodynamic hypothesis at the dynamic system. And of course, there is a mismatch. As black box function, I have used two techniques, two of the most important techniques used in literature. One is the MRF that has this structure. So it's a ratio is a ratio between two polynomials, and another one is the simple polynomial. So for this study, I have investigated two approaches, namely parallel and serial, where in the parallel approach, the two black box model, one describing the heat, the K of the heat transfer coefficient, and another one, the other one describing the deviation of the enthalpy are trained at the same time, and then the serial where the two models are untrained in two different times. This is to investigate about the impact of the cost function shape. Then we have the optimizer. One is the particle swarm optimization that my colleague Min has introduced before, and then another one is the differential evolution. The difference between these two is that in the particle swarm optimization, the solution that give the Ross results are still kept in the group, while in the differential evolution there is a survival approach. So only the best solution survive to the next generation. And then we have the two functional form that I have reported before. So we have 2 per 2 per 2. We have 8 combination of training approaches. Here in the slide on the left, on the right part, I have reported the training loop. So the optimizer will propose a set of parameters for the hybrid model to train. This set of parameters is implemented in the hybrid model, and the hybrid model is run by using the input from the company, the experimental input. So it will give an output that, of course, is a profile. This profile is manipulated in the way that is comparable to the experimental output. The experimental output is compared, of course, with the modeled output, and a fitness function value is returned to the optimizer. The optimizer correlates this fitness function value to the set of parameters that it has proposed at the beginning of the loop, and then it will propose a new set of parameters that hopefully will be better than the one proposed in the step before. As I have said, the cost function is an important parameter for our optimization, and it's reported here in the slide. As you can see, it has 3 main parts. The first one is the deviation of the temperature, that is basically the mean square error between the model and the experimental values. Then we have the receiver tank amount. This is more complex because, as I have told you in the previous slides, the evaporated amount bears of an underestimation because of this regulation in the vent gas, and I have estimated to be this loss the 10% of the amount inside the receiver tank. So if the volume of the receiver tank is in this error band, the function is punished with a power of 1.5. Otherwise, is punished with the power 2. Then we have the time to complete the process. This is needed to avoid that the chosen parameter are still letting evaporate the system, but the system evaporates too faster. So let's go to the results. Here in the slide, I have reported the overall cost function for all the training, for all the cost function and optimizer for the parallel training. In this plot, the lower are the value, the better is the search. As we can see, the MRF performs quite well on the training test, but when we are moving on the test set, it return values that are really, really high. This value is associated to a model that experience mathematical instabilities. For this reason, we have that the MRF are very bad in generalization. It means that if we give to the training set to the MRF, the case that they have experience during the training, they work well. Then when you change the exercise, they are not able to solve it anymore. This is not happening with the polynomial, because we can see that for the polynomial, both for the training test and for the test set, this function does not reach so high value. On the other hand, we have that the polynomial, it's also more robust because I have changed the initial position 10 times, and more or less the value returned by, by the differential evolution, it's more or less always the same also in the test set, while the particle swarm optimization return very noisy solution. So the differential evolution performs better than the particle swarm optimization. Here in the slide, we have the estimated K value, and we can see why the MRF are so bad in the generalization, because their solution diverge in a certain moment, while this is not happening for the polynomial. The fact that the solution diverge, so that they experience mathematical instabilities, is related to the fact that the MRF, they have a denominator. So the regime of the function now, the domain of the function is not the entire R, the entire group of the real number, but we have a subgroup. This is not happening on the polynomial. Then the differential evolution performs better in general than the PSO, because as we can see, the solution found by the differential evolution have more or less the same trend, while the PSO has also some outliers. Here we have the deviation of the enthalpies, and the same behavior is repeating. The MRF is not able to generalize, and it returns meaningless solution. The polynomial performs better than the MRF. The differential evolution performs better than the PSO. Then here we have the solution for the serial training. I want to remember that in the serial training, the two models are trained in 2 different times. So for this reason, the cost function is simpler to learn. And in fact, in this case, the MRF does not show the instabilities that we have seen in the previous slide anymore, and they are able to reach values comparable to the polynomial function on the test set. Then another good performance of the particle swarm optimization is that the particle swarm optimization now performs better than the differential evolution. This is related to the fact that the differential evolution eliminates the population that performs ROS, so it tends to overfit on the training set. And then also in this case, the polynomial performs really, really well. Here we have the modeled parameter for the serial training, and as we can see now, all the functions are able to get the right trend. However, the differential evolution polynomial combination is better than the other one, because the effect of the initial condition of the particle is less sensitive than the other cases. Sorry. This is about the deviation of the enthalpy, and we have this. We are experiencing the same case as before. So the differential evolution polynomial performs really well, and as we can see here, they are clustered all around one single line, and the width of the variance of this cluster is really, really low. Here we have a comparison between the parallel training and the serial training. As we can see on the train set, the parallel training performs sometimes better than the serial training, especially in this case, while on the test set, this is not confirmed anymore. Especially for the PSO MRF parallel, they shows a lot of outlier, and the box plot is really, really high. While when we use the serial approach, doesn't matter the approach and the optimizer that we use, the results are comparable. Here in the slide, I have reported the performance on the test set. I want to remark that this set has never been experienced during the training. So basically, in this case, you are explaining to the intelligence an exercise, and then you are giving a new exercise with different parameters. As we can see, and here we have, I have reported the white box model, the optimized white box model on this case that is represented by the yellow dotted line here, and the experimental data that is the blue dots here. The blue band here is related to the error. In general, as we can see, all the hybrid models performs better than the white box model. The only exception is the PSO MRF in parallel that shows a very high stability on the temperature, and it is not able to recover by this stability anymore. All the other performs quite well, and also here where I have reported the R squared, the determination coefficient, we have that the PSO has a very meaningless PSO parallel has a very meaningless R squared, while all the other are above 0.90 here. And in general, the serial performs better than the parallel, and the polynomial performs better than the MRF. Then I wanted to test further this model by letting him an experience by showing to him an example that is different from the exercise that I have proposed during the training set. And in this case, I have given to him a batch with the half of the original volume to see how it behaves. And we can see that all the hybrid model, especially trained in parallel, are able to follow the trend of the experimental data, and the white box model is performing really bad, so it's underestimating the evaporation. In this case, we have that if we rely on the white box model, we are selling on the market something that is that has still a high amount of DCM. So, in conclusion, the serial training is able to stabilize the solution. The polynomial stabilize the solution as well because it does not have the denominator, and the differential evolution performs better than the PSO. In general, I didn't add it here. When we are using a serial approach, the difference between the method is not so big, and the most robust and accurate training technique for this case was obtained by using the polynomial structure, the D-optimizer, and the trained in a serial manner. I thank you very much for your attention. If you have any question, I'm glad to answer. Yes. Yes, in fact, yes. In this case, the differential evolution required 4 times the time than the PSO, and then in general, the serial and parallel, etc., has a very negligible effect. It's minutes. While, for example, to train the model with the PSO, it took 2 hours in average, while the differential evolution takes 8 hours. So if I have to suggest to implement this model in a live system and so on, I would go for a PSO. If we have all the time, for example, we run it offline and we want to optimize it for a process that should be run in, I don't know, 3 or 4 days, we can use the differential evolution. Sorry. No other questions? Actually, the implementation of this is really close. I mean, this is with the optic to be implemented in a live way. Now, in fact, this is a part of a project in collaboration with an industry, and I'm taking care of the modeling part, while another colleague is taking care of the control part, because on this model, reinforcement learning is implemented, and it's really simple. The most difficult part is to identify which model, which part are having the deviation, and for this we need a chemical engineer, of course. Actually, it's a very good question. The scientific question is that I guess there is a bit of friction to implement this in real time because of GMP environment and so on. But I was reading a book for Jerry Kaplan, that is an AI guy from USA and so on, and he has studied a research from the Oxford University, and the line operator for chemical lines, pharmaceutical and so on, is one of the work with the higher risk to be substituted with the AI, basically. So my personal answer is I don't think in 10 years we will need a bit more. The scientific answer, I mean, from paper is yes. No other questions? Okay. Okay, so thank you very much.
Test? Okay. Okay, good afternoon. My name is Arne van Greef, and my PhD is about the continuous crystallization of pharmaceutical components. So to start off with the pharmaceutical industry. It's a massive industry with a yearly revenue of $1.3 trillion. That means that we pay a lot for drugs. And why is this? The manufacturing costs of drugs is $350 billion each year. And if we want to better understand this, we have to look closer towards how drugs are made. So drugs are made by using a wide variety of chemical reactions. And to give some flexibility, drug manufacturers use batch manufacturing to make their drugs. But continuous manufacturing doesn't have the disadvantages of batch manufacturing, of downtime, and so on. And a lot of other industries have already gone towards continuous manufacturing. And also for the pharmaceutical industry, it could be a big advantage. Estimates go that costs could be reduced up to 50%. We're talking 10 to hundreds of billions of dollars each year because of reduced labor costs, higher operational efficiency, reduced lead times, and so on. Now, to go even deeper into the pharmaceutical process, we can often distinct 3 stages in the pharmaceutical process. The first is the synthesis of the drug molecule. Then comes the crystallization of this molecule into the physical form we take in. And finally, the formulation into the pill form we all know and love. And this is where my PhD is about the development of the crystallization process and making it continuous. Now, why is the crystallization process so important? The drugs, or the crystals that are in the drugs, determine how well it will be taken up in the human body. There have been cases where the crystals weren't made well and they just didn't dissolve in the human body, and that's horrible. And also the crystals will determine the downstream processes in the pharmaceutical industry. So there are many important characteristics of the crystals that we make. So the crystal size distribution, the form, the yield, polymorphic form, agglomeration, they will all determine how well the crystallization step is. My research has mainly focused on one type of continuous crystallizer, and that's the tubular crystallizer. Why the tubular crystallizer is so good for continuous crystallization is because it has small working volumes, excellent heat transfer, narrow resonance times distribution, and these allow for conditions that allow small particle sizes, a big range of obtainable particle sizes, narrow particle size distribution, and high yields. Now, this sounds really well, but there are a lot of issues with tubular crystallizers that still have to be overcome before making it a viable alternative for the pharmaceutical industry. The first one is inducing the crystallization step itself, then controlling this nucleation, growth of the crystals to their final particle size, making sure that the whole process runs without fouling, and then finally analyzing our product. And with that one, I'm going to start. Because this one sounds really easy, but everyone who has worked with crystallization knows that the analysis is not as well as we would want it. There are a lot of parameters that we would want to analyze. Unfortunately, most techniques only analyze a few of these, or usually just one. And we work, therefore, on microscopy to analyze as much of these parameters as possible. So we used a microscope that we modified with a flow-through cell and a pulsating light source in order to make images of our crystals in flow while they were flowing. This is an image that we got of our crystals in a flow reactor. And for this, we made an image analysis algorithm to detect these particles. As you can see, the yellow lines here are the detected particles in this image. So, and with these detected particles, we can get a lot of information. First and foremost, the particle size distribution. This is the most obvious parameter. And then we have the number concentration. This is the amount of particles per unit of volume. And I don't know of any other technique that can get the number concentration in line. Then we have the nucleation rate, which we can get of the number concentration. The nucleation rate is a really important parameter as well which will determine the final particle size in our reactor. We also have the solid concentration, which is the mass of dissolved, crystals per unit of volume, and also the agglomeration degree. With these 5 parameters, we're able to really well define our crystallization process. Then going on to starting the crystallization process, because this is easier than it seems. When you build the continuous crystallizers, you can start 2 ways. You can start seeded, or you can use primary nucleation. Seeded crystallization works well, but has 2 advantages. It's inconvenient to provide a continuous seeding stream. And second, you're always limited in your particle size. You can't go smaller than your seeds. Primary nucleation is therefore an interesting alternative. However, there are challenges. Pharmaceutical compounds are very complex molecules, and in order to form a crystal lattice with these compounds, you need a lot of time. Time you don't have in a tubular crystallizer. Additionally, the nucleation chances in a small reactor are really low. Therefore, we need to be able to start the nucleation quickly. The most straightforward way of doing this would be by using high supersaturations. However, agglomeration, fouling would be the main issue there. And on top of that, even at high supersaturations, our nucleation rates are still just too slow. So we use 2 other techniques to eventually find a way to induce nucleation. The first one is ultrasound. Ultrasound creates cavitation, which is the formation of air bubbles in liquid. As I will show now, the bubbles oscillate, grow, and finally implode. This implosion causes nucleation, and this works really well. However, we still don't know exactly how it works. But what we do know is that it works. The second method is by using a rotor-stator mixer. Here you can see at the outer ring, which is the stator, the small gap, and the rotor. The rotor rotates at very high rotational speeds, 24,000 rounds per minute. And this creates a very high shear. And this shear starts nucleation. This is also a good method to start nucleation in a tubular crystallizer. Now, we've investigated both, and both are similar. They have their differences in how they work, but are both very well able to start the nucleation. But eventually, we chose ultrasound to move forward as it has anti-fouling properties, which is very important for a tubular crystallizer and which I will come back to later. Now, we know how we can start it. Now we have to control our nucleation. And when you design a tubular crystallizer, or any continuous crystallizer for that matter, you usually decouple nucleation from growth. So first, you create your nuclei, and those then grow in the growth zone to their final particle size. And the amount of nuclei that you make will determine that final particle size. Additionally, the amount of nuclei that you make will determine how fast they will grow. Because if there are more, they can deplete supersaturation faster. Now, the challenge is to get very high nucleation rates. And we also don't know which parameters influence this nucleation rate. So was the objective for this research. And the method that we did this by counting the particles that were coming out of our continuous reactor. So this is a method that hadn't been done before, and we evaluated the following parameters for the nucleation rate. And to summarize the results, supersaturation has a massive effect on the nucleation rate. Flow rate also has a big effect, and we also found that there was a maximum flow rate at which we could work. Ultrasound power also had a minor influence, but we did notice a minimum power for the ultrasonic power. The static pressure determined the ultrasonic power in the system, so it was also a relatively important parameter. Scale-up was achieved by keeping a constant residence time and using a constant ultrasonic power per unit of volume. And we also understood that the mechanism in a tubular crystallizer is not primary nucleation as we would expect, but secondary nucleation. So we have our nucleation under control now, then we have to go to growth. And how should we do growth? First thing what we know is that we need to have a constant supersaturation for growth. If we have a low supersaturation, our growth will be too slow and we'll be using our reactor inefficiently. If we are going to a high supersaturation, we'll have nucleation, agglomeration, and even worse, fouling. So we want to work at a constant supersaturation over the whole reactor. But how do we do this in a cooling crystallization? Well, if we are doing a cooling crystallization, we have to cool according to the cubic cooling profile, because which is the top one. At the beginning, we want to cool really slowly, because a small change in temperature will create a huge change in solubility. Additionally, the particles are still small, and therefore there's not a lot of surface area available to deplete your supersaturation. So we want to start slowly and then go faster. The issue is we usually get a natural cooling profile when we're cooling something to a certain temperature. This natural cooling profile is the exact opposite of what we want. And this is what we used, and if you look at it, it's the exact opposite, and this we use to actually get the cubic cooling profile. So we made the following heat exchanger. There's a heat exchanger with an outer heating jacket, and this heating jacket was at a high temperature. So warm water flowed through it at a high speed so that it didn't lose any temperature over the length of the heat exchanger. Then we added a cooling gas which slowly heated up because of the heating jacket to our final temperature. And if you look at it from right to left, it's heating up. But if we now enter something from the left, you can see it will cool down according to the cubic cooling profile. This is what the idea was, and this is the data. This is what we finally got from our experiments. The green line is our obtained cubic cooling profile. Now, with that in place, we went to a final work package where we combined everything together. So in this work package, we were working on combining the growth strategies and the nucleation strategies to get a full continuous process. And our goal was a process that could run at least 4 hours. 4 hours may not seem a lot, but there hasn't been any tubular crystallizer documented in literature that could run 4 hours. Additionally, we want to be able to have a controlled particle size distribution and get a yield of at least 90%. This is the setup that we used in order to try and obtain this. We start at the left with our suspension that's then dissolved inline in our dissolution bath. One of the two streams goes to the pulsator. The pulsator, as earlier mentioned by Joris, causes a pulsating flow, which stops sedimentation, agglomeration, and fouling. And part of the stream goes to the ultrasound. The ultrasound is for starting the nucleation. These streams are then combined together, go to the heat exchanger, where they're cooled down, the growth is done. And finally, we have everything crystallized, we filter it, and we analyze it. And we were able to obtain our 4 hours of residence time, or operating time, not residence time. And this was our goal. To get longer, we might be able to go longer, but at this point we can also use an intermittent cleaning without a yield loss. We also obtain the constant particle size over time of 140 micrometer and a narrow particle size distribution. Finally, we obtained high yields between 80 and 100%. And thank you for your attention, and I'm happy to answer your questions. Mm-hmm. Mm-hmm. Yeah. Yeah, indeed. The yield is compared to everything that's dissolved, or no, everything that can crystallize. Yeah. 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 Indeed. Yeah. Indeed. Yeah, I might have to specify the 80 to 100%. We're not entirely sure where it is. Our measurements weren't that accurate to determine if it's 80% or 100%. So it's actually that we don't know. Mm-hmm. About 33% of everything is still left, and that's not acceptable for industry. But this was, of course, a proof of concept. And in literature, you would, of course, start at the higher temperatures and try to crystallize out more. No, yeah, you would, of course, use a higher concentration that you could dissolve at a higher temperature. And then you go down, and then you crystallize, yeah, more. Of course, you can also go to a lower temperature, lower final temperature. That's of course more difficult because you have to cool below room temperature. Well, it is an interesting technique. We just chose for a lower supersaturation to start to get a better proof of concept. And in industry, our next step would be is to go at a higher concentration, start with a higher concentration, go to 80 degrees to dissolve everything, and then crystallize it, and then we would get a higher yield of 90% at least. But that's the next step. I would expect that you could at least obtain the same particle size distribution. Because for one thing, the nucleation that is done here, if we have more concentration, we can work at higher temperatures. We can also cool more to lower temperatures because we're limited in our cooling. So if we cool 80 degrees with something of 1 degree, we can go to 50 degrees and we'll get a supersaturation of 5, 6, which will cause a lot of nucleation, which is more than we have now. Therefore, we would have more seeding particles and we should be able to get at least particles of the same size. That might be that's something that you might expect, but actually it's the other way around. The more particles you have, the less fouling you have. Because if there are more particles, you can deplete your supersaturation on these particles. And the lower the supersaturation, the less fouling you have. Actually, we always noticed that if you had a higher supersaturation in the nucleator, that you had less fouling. And that's actually something that's really interesting and might have been, or might seem contradictory, but it's actually the case. Yeah. Mm-hmm. Yeah. So how would we do this? The advantage with cooling crystallization is that your mixture doesn't change. So what you would do is you would just heat everything up, put a recycle in, bring it back to the original vessel, dissolve everything, and then then you can clean everything. Since everything goes back to this vessel, the concentration doesn't change. And then you slowly cool everything down again and start the crystallization process again. And that way you can also prevent yield losses. So we change the temperature of the whole system. We heat it up to prevent or to remove any fouling. We can redissolve it. And then we just send it back and recrystallize everything. This is, of course, possible for cooling crystallization. For anti-solvent crystallization, this is not the case. This is a bit more difficult, and that should be approached in a different way. Probably either by using ultrasounds or using everything with ultrasound to prevent fouling. You can dissolve it, you can of course clean it with solvents, but then you have yield losses. It's always a tricky way to solve it. Yeah. Mm-hmm. Yeah, it's an arbitrary scale that I use because I couldn't just go over all the results here. But what we saw was that the supersaturation just had a very big effect on the nucleation rate while varying it. We varied all the parameters and we compared how much they influence the nucleation rate. That's how we got there. Sort of, yeah. Yeah. Yeah, indeed. To go a little bit further about that, you talked about a correlation. No, what was it? Yeah, correlation between the parameters. That's something that's still lacking from this research, and it's always interesting for further investigation. We investigated each parameter separately because it's quite a difficult research to perform. that was, of course, the initial idea. However, there are some, how do you say it, difficulties when trying to investigate these parameters, because it's really difficult to change one parameter without changing another one. If you, for example, change the flow rate through this nucleator, you will also change your cooling profile. And then you will change your supersaturation, and then you're changing two parameters at once. And then it becomes more difficult to analyze each parameter separately. That's the reason that we went for the approach that I just showed. Yeah. Okay, that's interesting. We have to talk about that later. Thank you. Thank you.
Okay, good afternoon, everyone. Today I will discuss my PhD topic based on injection molding polymer microneedles using laser ablated molds. So I'm sure everyone knows conventional hypodermic needles, and certainly due to this time with the corona pandemic and the corresponding vaccination campaign. But I'm quite sure that none of you, or almost none of you, will know microneedles, as are illustrated on the right. These microneedles are minimally invasive devices, which are usually arranged in an array and can be used to bypass the human stratum corneum skin barrier. And that is the upper skin barrier. Doesn't matter, you can see it on the right, which is quite hard to penetrate. What is the purpose of these microneedles? You can use it to deliver vaccines, drugs, antibodies, and so on to the human skin, or it can be used for sampling applications, to sample or extract fluids from the human body to analysis on, for example, on interstitial fluids or on blood. And what are the advantages compared to conventional hypodermic needles? These microneedles are pain-free. This is due to the fact that they are not long enough to pierce the nerve system. So when you pierce the skin, you will not feel any pain. And this reduces needle anxiety. You can use it to deliver vaccines directly to key immune cells, which are located usually inside of the layers of the skin. They can be used for self-administration purposes by a small disposable patch, for example. You can have lower storage, distribution, and disposal costs due to their small volume, and the microneedles also enable it to be included into a lab-on-a-chip system, where it can be used for sampling applications. And then inside of the lab-on-a-chip, you can do all kinds of analysis. The characteristics of the microneedles, you have up to you can have up to 2,000 microneedles per square centimeter, with individual needle lengths between 100 and 2,000 micrometers, and the tip should be sharp so it can easily penetrate the skin. There are a few strategies or a few different types of microneedles. The first one is the poke with a patch strategy, where you first poke your skin, create some pores into your skin, and afterwards apply a medical solution which will diffuse into your body. The second technique uses pre-coated solid microneedles. Here you pre-coat the medical solution on top of the microneedles, then you puncture the skin and the medical solution will dissolve once again. On the left, those two are both solid microneedles. Now on the right, there are the hollow microneedles, and these act in a similar way than hypodermic needles. They also have a lumen or a bore where the fluid can run through. On the left, you can see that you can apply or inject a fluid in your system or in your body. And on the right, you can see that it extracts fluid. At this moment, the current problem is that there is not a technique yet which can produce these microneedles in a cheap or a cost-effective way and for mass manufacturing, so at large scale, large number of products. And therefore, we first developed a method to produce solid microneedles. This technique uses a femtosecond laser or a ultra-short pulsed laser, which creates microneedle cavities, so the negative of the needle, inside a metal insert. This insert is then placed in a mold housing, which is then used in an injection molding process where the microneedles get replicated. For the laser machining strategy, I will not go into too much depth here, but as I have already said, it's a femtosecond laser, and we developed a cross-hatching strategy. The cross-hatching strategy is displayed here, where each line represents the path of the laser. So the laser will follow each line within the circular region. He will scan the circular region once, and then the focal point of the laser is lowered, a certain dimension being the layer pitch, as you can see there. And the same process is repeated, and this can be done for a number of times, defined as the number of layers. And using this technique, we can create microneedle cavities in metal inserts. As you can see on the right, you can see a XY CT slice of a steel insert of 3x3 microneedles there. The laser machining is done at the Ceres in Diepenbeek, and the micro CT was done in MTM in Leuven. Then once we have these microneedle cavities, we want to replicate them. And here you can see our injection molding machine, which was used for this. The cycle time for producing a part is around 15 seconds, can be lower, can be a bit higher, depending on the process conditions. And the process conditions are very important. You need elevated process conditions, high temperatures, high injection volume rates, high pressures, and so on to achieve a good replication fidelity. And on the right, you can see this replicated part, the replicated polypropylene microneedles, having a replicated volume of about 70 or 97%. Now we want also to control the geometry of the cavities, so we can also control the geometry of the replicated needles, of course. And here we varied two parameters, being the programmed base diameter and the number of layers. And this was done, or by doing this, we achieve 16 different sets of microneedles with different settings. This matrix was placed then on a sample, and here you can see the part having 60 by 50 millimeter in size. This was done for 3 mold materials which are commonly used in injection molding, which is tool steel, copper alloy, and an aluminum alloy. Here you can see the outcome of the laser ablated microneedle cavities inside of the 3 different mold materials. Do I have a laser? No, I don't think so. I have. So here you can see on the y-axis the base diameter, on the x-axis you can see the amount of layers, and then you can see this is for tool steel, copper alloy, and aluminum alloy. And at first you can see that with higher number of layers that the depth of the microneedle increases. So for example here, the number of layers increases, the depth of the microneedle also increases. Yeah? But there is a certain saturation. Here you can see, for example, this microneedle and that microneedle are almost the same depth, and here you can see that these microneedles also have a similar depth, which occurs after a certain number of layers. Then, a second thing that we can observe is that there is a difference in shape and dimension between the 3 different mold materials, and this is due to differences in material properties. Then we can replicate these microneedles and see if there is a difference in the replication fidelity. And here you can see a replicated part, also in the microscopic image. And on the right, you can see the replicated microneedle inside of the corresponding microneedle cavity. As you can see, the microneedle is quite well replicated, and it has a very sharp tip. Furthermore, we also want to evaluate if we can change the geometry of the flank. So basically, the flank geometry here, can it be adjusted? And that's the next question. And here we have design 1, which is the reference design, which is the conventional method, which I already explained. And in design 2 and 3, we varied the base diameter throughout the ablation process. So here the second design is to intend the intent is here to widen the microneedle base, and this was done by increasing the programmed base diameter in the first few laser layers. As you can see here, we start by lasering a larger circular region and then go back to our reference design. In the third design, we want to decrease the diameter throughout the length, the diameter of the needle. And this was done easily by decreasing the programmed base diameter throughout the layers. Here you can see the results. The first one was the reference design. The second one here was the intent to widen the base, which you can see is successful. And then the third design, we wanted to decrease the diameter throughout the depth, which is also successful. And on the right, you can see the 3 designs which are replicated in polycarbonate, which is a or a grade which is biocompatible and could be used in the actual application. Then we are also interested in being able to model or to simulate the replication fidelity using a software program. Here we used Moldex 3D. And this is due to the fact that once we adjust some parameters in the injection molding process, or if we want to evaluate different geometries, it takes a lot of time to evaluate and to find the replication fidelity. And as I already said, we can change the geometry of the micro features, the processing parameters, and also the polymer and mold material. And those will all have an effect on the replication fidelity. Here you can see my mesh, and I used multi-scale meshing with a mesh refinement near the micro features. As you can see here, a lot of elements are inside of the micro features, so we can achieve an accurate prediction there. The similar or the same part as I illustrated before was here used for the simulation process, and we used the micro CT slices as input to create a CAD file, which is afterwards used in the simulation. Of course, the process conditions and the materials were identical to the experiments. And then one important note is that we varied the heat transfer coefficient. And basically this heat transfer coefficient is a parameter inside of the software which you can adjust and found in literature to be very important for micro feature replications. Most of the people or some authors or some researchers vary this parameter to achieve a good replication fidelity. So this is basically a parameter which is used to tweak the process to achieve good results. And when we looked into the replication fidelity, we can see that the green dots are the experimental values, the blue dots are the simulation values, and this is the replication in height and percentages. And here you can see the aspect ratio of the hole of the microneedle cavity. And you can see that the simulation correlates very well with the experiments, both for polypropylene and for polycarbonate, when using a heat transfer coefficient of 10,000 watts per square centimeter Kelvin, and for polycarbonate at 30,000 watts per square meter Kelvin. How does this simulation look like? It's something like illustrated here. You can see the filling, and then we can look closely into the filling inside of the microneedles, and then we can assess them once the injection molding process is finished. So here you can see a slice through the microneedles to assess the replicated height of the microneedles. Then this was my first talk about the solid microneedles. The second part is on hollow microneedles, and this is basically somewhat the holy grail yet still to produce these parts at a high, or to mass produce these parts at a low cost. And here we started from a similar strategy, but now our laser machining strategy is adjusted a little bit, which I will explain in a bit. And now we create hollow microneedles, which have a lumen, here a lumen diameter of 100 micrometer. At this moment, the microneedles are hollow. As you can see, the needles itself are hollow, but these microneedles are mounted on top of a solid flat plate. So the plate where they are on top of is still solid, and therefore we need to drill a connection through the plate to the microneedles. This additional step, this micro drilling step, we want to avoid this step or eliminate this step in the future by adjusting the mold design. But this is quite costly, and we will do this once we have a microneedle design which can be used in the actual application. And at last, we have these hollow microneedles on top of a plate with a fluidic connection. The laser machining strategy is similar to the one that I just explained, but now we have a internal scan-free area which will form the lumen or the bore inside of the microneedle. So here is still the remaining material, which is the result of this internal scan-free area. We also replicate these microneedles using injection molding, and here we assessed different parameters, being the injection temperature, volumetric injection rate, holding pressure and mold temperature, and we created 3 sets of injection molding conditions, being low values, middle values, and high values, just to show or illustrate the importance of using good injection molding parameters. And this was done for polycarbonate grade, which is usable or which can be used in medical devices. Here you can see the outcome, where you can see on the right, maybe it's interesting to see, that there is a big difference in the replication fidelity. The needles created with high injection molding process conditions have a good replication fidelity, which is also observed here on the left. A replication in height of about 80%, while the low conditions it's only 50%. And also important, the tip thickness, so basically how sharp the needle is the lowest at the highest injection molding process conditions. How do these microneedles look like in 3 dimensions? That can be seen in this movie, where the shape is quite similar to conventional needles, as they have a bevel-shaped, or as they are bevel-shaped. The microdrilling step was conducted in Leuven at Werktuigkunde, using the Kern MP milling machine, and we drilled holes to create these fluidic connections. Then, together with Mebius, we created a microfluidic chip where we assembled the microneedle array on top of a fluidic or a microfluidic chip. As demonstrated here with double-sided tape, we mounted these microneedles on top of a top layer. Then we have again double-sided tape where the microfluidic channel is cut out and a bottom layer, and when we stack these together, we can create a microfluidic chip in a quite easy way. On the right, you can see this microfluidic chip in real life. Then we can use some colored water, for example, to flow the water through the microneedles. And on the next slide, you can see a quite advanced microfluidic chip, which is autonomous, so it doesn't require any source of electricity or any energy source. It is just by finger actuation that we can let the injection go through. So I will start the video. As you can see, I pushed with a finger actuation on this activation button. Then the working liquid gets in contact with a porous material, which is a sort of paper. Because this paper sucks up the working liquid, here a pressure is created. This fluid, which is needed to be injected, gets pushed to the microneedles, which are below this small weight. And the microneedles are injected or punctured in an artificial skin model. And here you can see that we are injecting the fluid inside of the artificial skin. So there is still some work in progress. We still need to optimize the replication fidelity in the injection molding process. And then my colleague Paul is working together with me on developing a new mold design to remove the micro drilling step. Then we have also a master thesis this year which will do research on characterization of the mechanical strength of the microneedles and also on the insertion forces of the microneedles into skin and to start, of course, into artificial skin. And on future plans, we still want to assess the functionality of the microneedles in further depth. Then we also, or Paul, is creating a model to predict the shape of the laser ablation process. And then at last, we also want to optimize our hollow microneedle design. So I want to thank you for your attention, and if you have any questions, please. Yeah. Mm-hmm. Yeah. So basically, it depends also on the size of your array. Usually, you place these microneedles in an array, which can be, as I said, up to 2,000 microneedles per square centimeter. The more microneedles, of course, the more injection you can create. Yeah. Yeah, that's a quite interesting question. I'm not a medical expert, so my guess is that these medical solutions should be adjusted to be able to be used in a microfluidic setup, but I'm not quite sure. So yeah. Yeah. So the process is not optimized yet. So we still need to optimize the injection molding process to achieve hopefully higher replication fidelities. Achieving a replication of 100% will, of course, be very difficult, as you then can, or it can occur that the microneedles get stuck inside of the molds, and it can be hard to detach or to demold the microneedles. But I think, and it's also depending on process conditions and material, that you can still achieve a better replication than 80%. Yeah. Yeah. So by using a different technique, indeed, as you recall, injection compression molding, it could be beneficial to have a better replication fidelity, but also a better replication fidelity over the part, a more homogeneous replication of the microneedles over the product, let's say. That there is no difference between microneedles located at the end of the product and microneedles located at the beginning of the product. Mm-hmm. Yeah, no, that's true. The replication fidelity, or at this moment, the importance is that the microneedle is functional. The design that we have is just a first design, and the intent is to have a functional microneedle. And it could be, or it could well be, that a functional microneedle is reached at a replication fidelity of 80%. But the aim should be to create a functional microneedle which is sharp, which can easily puncture the skin, which has a high mechanical strength, so it doesn't get deformed during the application. Yeah, and that there is no leakage or backflow, that the liquid can easily pass through the needles, and there is no leakage between the skin and the needles. So it's basically depending on the design that we intend, then we need to assess if we can adjust the mold to incorporate already the bad replication or the incomplete replication. To model it. Mm, I think it would be doable to create some kind of model or to simulate a strength and the functionality, but that's a PhD on its own, let's say, because, for example, to model the functionality of the skin, that is still a very, very hard topic, and then this model is needed to simulate the penetration force, for example. You could try to increase the strength of the needles, but that could, as a downside, mean that the needles are not sharp enough anymore. So there needs to be a correlation between sharp needles and also strong needles. And okay, there could be a study on this, and but at this moment we approach it at first as experimentally. Yeah. So the part that we did here was purely experimental and based on experience, which I had with the previous study. Here we varied 2 parameters, and then we knew what the outcome was. That if we increased the programmed base diameter, that we achieved wider microneedles. So in that sense, we already knew that we could trigger or that we could adjust the microneedle shape, but we were not yet, or we did not yet know if we could trigger it in how do I say it? In a variable way that we changed it throughout the depth. So yeah. Because at this moment we have changed some injection or some laser parameters, but as you can see here, and this is only for the solid microneedles, you have 1, 2, 3, 4, 5, 6, 7 parameters which you can adjust. And therefore indeed Paul is coming up or creating a model to simulate this. A lot of challenges. Last question. Okay, thank you.
I hope it's not too loud. Okay, I will go back to the title slide. So, good afternoon, everyone. I am Femke de Bie. I'm a PhD student at Celkunststoffen, and today I will be presenting my PhD research on acoustic metamaterials. And the title is already a little giveaway on what this presentation will contain. So, acoustic metamaterials, of course, refer to sound, and it's good because it will act as a solution to current problems in that field. So a short overview, I will first give a little bit of information on the project motivation, then go to the state of the art, share some research results, and then focus on the future work. So first, the project motivation, the noise problem. Over the years, we have seen a drastic increase of the daily sound pressure level that one is exposed to due to several reasons. For example, urbanization, so the fact that the world population grew and people started to live together in large cities. Secondly, we also have transportation, so aviation industry, railroad traffic, regular road traffic, trucks and cars. And we also have, of course, the technological evolutions, so company and industry, cell phones, office equipment, ventilation, etc. And all these things have led to the fact that today environmental noise has become the second largest cause of ill health in Western Europe. For example, accounting for 12,000 premature mortalities each year, or 12,500 children suffering from cognitive impairment also each year. So these numbers are not so positive, and it is assumed that, of course, the problem will be even larger if we would also consider indoor noise, such as me speaking to you right now. One way to solve the noise problem is to focus on sound absorption. And sound absorption is actually the process of lowering the sound pressure level in a closed environment, such as offices and factories. So what do we have? We have a human in a closed environment with a sound source. You have the emitted sound waves. These are partially reflected on the walls and partially transmitted. And by using a sound absorption material, the reflective sound waves, so the total sound pressure level inside the room decreases. And within this project, we focused on the 500 to 2000 Hertz frequency range, as we know that a lot of daily sound sources emit sound waves within this range. What are conventional solutions or conventional sound absorption measures? At first we have porous layers, such as foams, and these layers realize effective absorption of frequencies for which 1/4 of the wavelength is lower or equal to the thickness of the layer. And here an absorption curve of such a porous layer is shown. So on the y-axis we have the absorption coefficient, so the amount of sound that can be absorbed by the structure, and on the x-axis we have the frequency. And we see that porous layers have a very broadband effect, meaning that they can realize high absorption over a broad range of frequencies. But the large disadvantage is that they become very bulky at low frequencies because of this rule. An alternative are resonators, and within resonators we can divide resonators into two main concepts or categories. We have at the left Helmholtz resonators, and on the right we have so-called quarter wavelength resonators. And with resonators, the absorbed frequency strongly depends on the geometry of the absorber. The major advantage is that they are very well tunable, so they can be very well tuned to absorb certain frequencies. And being so, they can be more compact than foams while targeting the same frequency. The disadvantage is that they are very narrow band. As you can see here on the absorption curve, you can see that absorption is realized in a very narrow frequency range. So of course the question is, how can we realize compact and broadband low frequency absorption at the same time? And that solution, or the answer to that question, can be found in what we call acoustic metamaterials. And I have an acoustic metamaterial with me. This is what an acoustic metamaterial can look like. So it's a structure that can provide compact and broadband absorption by combining different folded and or coiled resonators together. So this is what it can look like. So a short overview on the state of the art. So what is the current situation? Here are some examples of acoustic metamaterials that can be found in literature. So on the top left we have a modified Helmholtz resonator. In the middle we have a quarter wavelength resonator that consists of 2 coil channels back to back. On the right we have a hybrid structure, so where Helmholtz and quarter wavelength resonators are combined. On the bottom left we have a special, a rather or a more exceptional shape where we have a main pore and different side branches. And on the top right we have the design that I just showed you. If you want more information, the literature is listed here and can always be consulted if you like. So despite that acoustic metamaterials have been studied in literature, they still aren't used on a more larger or industrial scale. And this is due to 3 main reasons, or still 3 main reasons that are listed here. So we have modeling, manufacturing, and validation. So on the modeling, as you can see here, this graph shows the absorption behavior of this folded design, of actually the same design but then unfolded, and also our analytical of theoretical prediction. And we see that there's a difference in absorption behavior between the folded and the unfolded design, and also between our theoretical prediction and our experimental results for both designs. So the current analytical models that exist are not yet fully capable to accurately predict all aspects that come with the manufacturing of acoustic metamaterials. So this is something that we will look at into our research. We will also look at manufacturing. So current acoustic metamaterials are mainly most often produced using additive manufacturing, so FDM, fused deposit modeling, which is a great technique as it allows to produce complex shapes in one time. But at the other hand, it's still rather expensive, and it has still a relatively low geometrical accuracy as compared to other more common production techniques. The manufacturing aspect will also be looked at. And then lastly, validation. So as you can see here, and as you can see here, tests have now mainly been performed on sample level, so on little structures that are tested in lab conditions. And we have not yet validated acoustic metamaterials on a larger, more real-life scale. So that's the third part, or the third issue that we will tackle in this research. What have we done up till now, or what have we obtained up till now? So the first goal that we defined for ourselves is to create an accurate, versatile, and computational efficient modeling framework that allows us to predict the absorption behavior of acoustic metamaterials using analytical models. We want to do this for single, parallel, and serial ducts, and also for different duct geometries with a constant cross-section. We want to check or validate these models using numerical simulation in COMSOL. We will compare these results with acoustic metamaterials concepts that can be found in the literature. And we will conclude, or we want to conclude with conclusions and the main takeaways that we will use in our next steps. So a little information on the basic analytical models. the phase I'm in now, or the models I have been using now, can be applied for quarter-wavelength resonators. And these analytical models actually just find a solution to the Helmholtz equation, which is the steady state equation to the wave equation, or the Helmholtz equation actually describes the wave motion as a function of the position. And here you have the two unknown parameters, so the density and the bulk modulus, and expressions for these values are derived in literature by, for example, Stinson, Allard and Atalla, and also Krex and Hildebrand. So ready-to-use expressions can be found. These two expressions, or these values, are then used to calculate the impedance and the wave number. The impedance is a measure of resistance that air sees when it goes through a pore, or when it goes through the resonator, and then the wave number is needed to describe the wave motion that occurs within the pore. And then these two parameters can be used to calculate the total resonator impedance, which can then be used to calculate the absorption coefficient. And this coefficient is then plotted as a function of frequency to give the absorption curve. Several absorption curves are shown here. So the first one is just just that we implemented the model for a single resonator with a circular aperture. So so the sound waves in seed, and then the absorption happens. And by this geometry, which has arbitrary dimensions, realizes perfect absorption at around 800 Hertz. By extending that model to also different geometries or different shapes with constant cross-section, it's possible to compare the performance of several resonators. So for example, the blue one is for a circular, the red one is for a triangle, the orange one is for a rectangular, and the black one is for a slit-like pore or slit-like resonator. And by playing with the dimensions, you can find a geometry that performs best given a certain targeted frequency. But as you can see, these are always single resonators, so they only realize absorption at one frequency. Of course, it is our aim to realize broadband absorption, so we'll have to use multiple resonators together, and that can be done either in parallel or either in series. Here I modeled a parallel resonator with slit-like pores, and then you can see that you can realize broadband absorption from around 600 Hertz to 1000 Hertz. And you can also place several resonators in series, and then this absorption pattern is obtained. And then of course you can go further by combining serial resonators in parallel, and then you can go technically as far as you want to go. So these are just some first results based on literature that we could find. We also benchmarked our results with literature, and very good matches were seen. So the models that we implemented are assumed to be correct. But of course, we also plan to do a numerical simulation and compare our analytical models with this simulation, because when performing a simulation, additional physics are taken into account. For example, as you can see here, multiple resonators are combined, so it's possible that they interact with each other, which might influence the eventual behavior of our absorption. These effects are not included into our analytical model. Also, so-called end corrections, so our air goes from an almost infinite air domain into a very small pore, so there might be some effects that occur in that transition area that are also not included into our analytical model, but of course are present in our numerical results. And as you can see, we have some deviations, and of course the reasons for these deviations will be investigated. It might be due to inaccuracies into our modeling, but it might also be due to additional effects that we have to further investigate. So the future work that I planned, there's still a lot of work to do. So we plan on further benchmarking models with our experiments. We also want to extend the modeling framework. As I mentioned, I've been working now on Carter wavelength resonators, but we will also look at Helmholtz resonators and of course hybrid structures. The analytical models up till now have always considered straight pores, so the unfolded version, while in reality our pores will be folded or coiled. So we have to find expressions that can account for these changes. We also have to include production parameters. For example, when you 3D print a certain geometry, you always have a minimal wall thickness that you have to respect. You have to change your geometry accordingly and see what that effect might be on the behavior. You also have, for example, rounding, so you won't have 90-degree corners, but there will be a little radius of curvature that you have to account for, etc. That will be done here. And then we will also do geometry optimization. So if we have a certain sound problem, what are the most optimal parameters for our design to realize best possible absorption? And then of course the real-life validation and also valorization of acoustic metamaterials. For example, as partition walls in landscape offices, as furnishing, for example, in auditoria as here, or in machine housing or any other areas where noise might be a problem. That was it. I would like to thank you for your attention, and if you have any questions, feel free to ask them. Any questions? Yes. 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 No, I just worked with the test infrastructure that was present, and we didn't change anything. It's calculated within the software that we use. So we have an impedance tube, which is a tube with a certain diameter. Then we have a sound source at one hand, and then the metamaterial on the other hand. And then signals are sent out, and then based on 2 measurement points. So we have 2 microphones measuring pressure at 2 different points. Then the measure is present, and transverse functions are calculated, and based on those functions, the absorption behavior is predicted. Yeah. Yeah, sure. Mm-hmm. 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 Yeah, as you point out, when we go to rooms where acoustic is important, for example, theaters, but also studios where music is recorded, etc. Of course, there you have to be careful that you find the balance between the right acoustic, that everyone can hear the people on stage, but also that other sources of sound do not disturb, do not disturb the experience. Yeah, and as acoustic metamaterials are specifically focusing on these low frequencies, so on these bars, it might be possible to use acoustic metamaterials. But yeah, when we talk about bars, it's in the very, very low frequency range. So it might be even maybe lower than 100 hertz up to 200 hertz. Those are frequencies that we will not look into our research, or at least not explicitly. But yeah, it can be possible that acoustic metamaterials can be used for those purposes as well. Ja, nog een vraagje? Ah, yeah, sure. Yes? Yeah, that's a very good question. It's of course when you have a certain situation, for example, in a room, it's important to determine how many sound absorption material that you need. And there is a rule depending on the sound burden, so the amount of sound that's present. It can be up to 10%, but it can also be up to 30 to 35% of the walls that you need to cover to effectively absorb sound. And then, yeah, depending on the eventual design and the eventual performance, it might be possible that you have maybe 10 metamaterials on 1 squared meter. It might be more. It's very dependent on the situation itself. So it's not a fixed number that you need. It's very depending on what problem you want to solve. But one sample isn't enough. You will need more. That's for sure. Yes. You're talking more about the mechanical strength and everything. No, that was not accounted for, because we are here only speaking about acoustic metamaterials. The structural part is more covered by Christophe, who will talk about vibroacoustic metamaterials. But here it's very much the structure and the air itself. So yeah, as you may find, these are very light. So you don't need an enormous structure to keep them up. Yes. We hope to look at more high throughput production techniques, such as injection molding, where we're working on within the research group, but also machining, maybe laser cutting if that's an option, just other production techniques as well. It's not that additive manufacturing is complete out of the scope. If we find that with using additive manufacturing there can be a considerate improvement in absorption behavior, then we will of course go for additive manufacturing. But if we have two designs, for example, one with additive manufacturing and one with injection molding, and they perform the same, then yeah, the injection molded design will most likely be less expensive, so we will choose that one. Yes. Those are not considered in the models themselves. So as you might, I have to go back. So for example here, the frequency, for resonance-based concepts at least, the frequencies they target is only dependent on the geometry, so only on the cross-section and the length, and here on the volume, the neck, and the length of the neck. So the parameters of the materials themselves are not directly incorporated into the model, but it can play a role, but that's not yet included. Yes. Yeah. So yeah, it's you here have the equivalent density and the equivalent bulk modulus. So the equivalent refers to the fact that it's that it refers to the air into the pore, so not the air in an infinite domain, but really in a very narrow region where you have viscous and thermal effects that occur and that can influence these values. And the tilde here refers to the fact that it's dynamic, so it's frequency dependent. And when you will look at the expressions for rho and for k, you will see that they are mainly dependent on the frequency, as I just said, and also on the geometry of the pore. So for circular on the diameter, for rectangular on the side lengths, etc. But yeah, I don't know them by heart, but those parameters are certainly included into these expressions. Any other? Yeah, Elke. Okay. Yeah. In these models here, they assume a so-called motionless skeleton, which means that the structure itself stands still, but the air in the structure moves. But for I think it's frequency. It's a so-called decoupling frequency. I don't know the details. But when that frequency is passed, you will have to use so-called biome models, and these models also assume that the structure moves. And when the structure moves, of course, the properties of the structure itself will be more of importance to the total behavior, I think. Yeah, but normally the frequency limit is out of scope for our project, so it's safe. So within the frequencies that we assume, it's safe to assume that our skeleton is motionless. But if you go outside that scope, it can be that the skeleton also moves, and then you have to consider the structural effects as well. I didn't look into biome models into detail, so I can't give a decisive answer. But yeah, Elke can help you if you want. Yeah. Any other questions? Yes. Can you clarify? I'm not sure that I totally. Yes. The absorption is only dependent on the frequency. So as I said here, the frequency that the geometries work on are only influencing the frequency, But of course, as you would increase the volume, then the intensity or the sound pressure level coming from the incident waves would increase, and having the same amount of absorption, the sound pressure level in the room would be higher, but just because these waves are louder. These are the same, but these are louder, which makes that the total sound pressure level increases within the room. That's of course something that people have to mind, that it would not give them a safe or a false sense of security. It's not that they can tune their radio wide open and have no damage to their ears. That's of course not the case. If you increase this, and this is at maximum, it's not. Okay. Yeah, sure. Okay. Any others? I think it's time. Yeah. Sorry.
Nee, dat gaan we niet doen. Hè. Okay, so you all hear me, I assume. Okay. Thank you. Okay, so I'm going to start because first I have to thank the two previous presenters, because Tim already showed you the concept of injection molding and Femke told you that noise is a problem. So now I'm going to combine the two of them. I'm going to tell you a bit on my work on vibroacoustic metamaterials, where I mainly looked into the injection molding of resonators. I will explain in a minute what that's about. So first, I'm going to start with a small, the context and the motivation for this work, whereafter I will explain what these kind of metamaterials are and how they work. And then immediately the main challenges will pop up, which we need to face before industrial breakthrough will come. And then I'll show you the progress I made. So I made a benchmark study, or I'm working on a benchmark study, where I look towards the injection molding process, and I also worked a bit on the link between the product dynamics and the injection molding process. And then finally I'll wrap up the most important conclusions. So first, why this research? We have several environmental problems and health problems we would like to tackle, or a combination of both. First, of course, air pollution. What else? So due to CO2 emissions, as you can also see in the picture, air gets polluted. And as a solution for this, there's a strong trend in industry towards lightweight design. So we try to make lightweight structures so we can remove mass from the logistics chain, which is beneficial for economical and ecological reasons. You can also see that here, this is a lightweight material market. So you see we have a trend towards lightweight design, and all these structures we make are typically light but have a high strength because they still need to be strong, so to say. So the stiffness to mass ratio of all these products is increasing. Then we have the second problem, so the noise problem. I do not have to mention you why, because Femke already did. And we see that for these structures with these high mass of stiffness to mass ratio, basically the transmission loss is decreasing. So what that means is that these light structures easily radiate sound. So the solution for our CO2 problem is actually enforcing the noise problem. That's also called the lightweight problem if you would look after. So we actually need lightweight noise and vibration solutions. And that's of course where locally resonant metamaterials come into view, otherwise I would not be here today. So here I have an example of a locally resonant metamaterial plate. So it's just a plate with some weird structures on it. I will explain that in a minute. And we see here in the velocity response that at a certain frequency we have a strong vibration attenuation. And that's of course highly interesting. So in this zone, we have no free wave propagation possible, and that's what we call a stop band. Now, how are these stop bands created? Therefore, I'm going to zoom in on one unit cell. So basically, this plate is a periodic grid of weird structures. I'm going to zoom in on one unit of this. That would look like this. So you see here, again, the same geometry, so to say. And you see that by adding these kind of mass spring elements, so resonators, on the host structure, on the host plate, we can create stop bands. It's important to say that we need to do it sub-wavelength. So we need to add these structures sub-wavelength with respect to the waves or the vibrations we target in the host structure. The good news is also that we can predict the stop bands. So based on finite element simulations, we can simulate the resonance frequency and then also predict the stop band. That would look like this. So we call this dispersion curves. I'm not going to go in detail on this, but what it basically means is that on the horizontal axis, we have the wave propagation directions, and then the blue lines are all wave solutions. And then we see at a certain frequency, we can walk over all directions without crossing a wave solution, so no wave propagation, no waves. Again, the stop band is found. What's very important to this is that we can do the predictions, so we can predict the stop bands and so use that for the design. But when we go towards manufacturing, small deviations in the resonator geometry, the resonator mass, or the material properties, which can be introduced due to the manufacturing process, immediately lead to another LRM performance. So that means that our predictions are worthless if we cannot incorporate the manufacturing process or inaccuracies due to the manufacturing process. So this is basically the concept of our locally resonant metamaterials. Now I have a few examples to show you, and then immediately we'll see some challenges. First example is made by additive manufacturing, is this enclosure. And yeah, I have it here, so normally I should be able to demonstrate you, but I'm not quite sure as the function generator is very unstable. But I have here a quite annoying tone, as you can see, and here I have just a random box of wood. I can place it over. The tone is still here. It's still quite annoying, so I'm rapidly going to the metamaterial box, which you can see here. And we hear that the sound is there are no vibrations because we are in the stop band, of course, and you can hear that it's much better. So we can also use this in our bus. So that's for the enclosure. Here, that's also to say is that this is quite a complex geometry. Here, the resonators are very nice integrated in the structure. We can also do more like add-on solutions where we just add the resonator on a structure like the plate I showed before. This is, for example, on a Range Rover, on the shock tower. So also to reduce vibrations coming from the tire and the road. So what I need to say is that, of course, additive manufacturing. So the first problem is that no mass production is possible at a low cost. And also the performance is off design. So as I mentioned before, small deviations in the geometry or in the material properties already lead to another performance. So what we need is multiple iterations. We design, we produce, then we see that the stop band is not where we expect it to be, so we need multiple design iterations with additive manufacturing. Another approach is a thermoformed panel, which we have in our research group. So this is actually a roof panel from a harvester cabin, I should say, yeah, so that's also close to a bus. And also here you can see spread on the resonator, so due to the local thinning in the sheet. So here again, off-design performance was present. There are multiple other techniques used, like laser cutting to cut out resonators and then add them on. And also injection molding was already demonstrated, but there's no research on how accurate the process is and what's the influence of several process settings. So that was not is not yet research, I should say. Then I have a small, so based on these examples, you already see some challenges we have. So first of all, mass production. We want mass producible at low cost, of course. Then we want this robust performance by design, so without all the iterations. And we also would like to make complex geometries, so more like the integrated structures and not all the add-on solutions. And here we see, if we compare several production processes, that actually injection molding complies quite good to these challenges. So that's one of the reasons injection molding comes into view, and we would like to investigate that further. So to wrap up my introduction, we want lightweight noise and vibration solutions, so we want stop bands, so to say. And we have challenges, so mass production, robust performance, and integrated structures. And then we saw that injection molding is quite a promising manufacturing process. So let's move on to the progress I made. So I began with the benchmark study. The aim of that is actually twofold. So first I want to know how repeatable is the injection molding process. Is there a large spread like there is with additive manufacturing or not? And then second, compare the injection molding process with additive manufacturing and also identify the most influential parameters of the process on the product dynamics. So what did I do? I just designed some resonator shapes, produced them, and then measured their resonance frequencies, so their dynamic response, to see what the spread was. So I had several designs which are commonly used, and I tailored them for injection molding, so some draft angles and some roundings were provided, and I injection molded them with PP and ABS. And then I have like this design, so a beam, a ring design. Someone also called this a cowbell, I don't know why. And then I also have a double beam design. And then the inserts, so mold inserts, were manufactured here in Diepenbeek by Simon, so thank you for that. And then we also see that the yellow crosses represent injection locations. So I have multiple locations where I can inject the polymer into the cavity and make these kind of products. So then the first measurement results. So for the beam resonators, you see immediately that in terms of mass, the ABS performs better with less spread than PP material. That's due to the lower shrinkage of ABS. And in terms of resonance frequency, it's more or less the same, but also ABS performs a bit better here. Then we see that there's not really a difference between the injection point. So both beams were filled well, independent from the injection location. But in general, we have a robust performance. We have not quite a lot spread on the resonators, especially compared to 3D printing, which I will show a few slides further in this presentation. Then for the rings, you also see that for ABS, there's a very small spread, so it's actually very repetitive. For PP, in case of food injection, we have a large spread on the mass. So how does that come? I started injecting in the food of the ring, so then the ring arms were filled, and at last the mass should be filled. But before the mass was filled, the beams already start solidifying, avoiding the mass to be filled correctly, so that looks like this. So here I had a shrink hole, and that causes a larger spread on the product. So we have to look out for this. We have to be sure that our products are well designed and avoid these kind of shrink holes. And then also the spread on the PP samples can be a bit larger in terms of resonance frequency due to the semi-crystallinity of the PP material. And then for the double beam designs, again, ABS performs more with less spread than PP does, but still quite some satisfying results for our applications. Then last, I compared the injection molding process with 3D printing. So I used fused deposition modeling to print some beam resonators. And here we again see that in terms of mass and resonance frequency, the injection molding outperforms 3D printing, so significantly smaller spread for injection molding. So to conclude the benchmark study, we have a very robust dynamic performance of the injection molded products, but we need to ensure proper product filling, of course. And we see, depending on the material, that there are some deviations, which can be caused to deviations in shrinkage and also the semi-crystallinity of the PP material. Next, I also told you I looked into the link between the product dynamics and the injection molding process. So remember these dispersion curves. We want to predict the resonance frequency on forehand to be able to make fast designs. So therefore, I just have the geometry, mesh it, and then calculate in Siemens NX the resonance frequencies. And I want to know how accurate are these models, and can we update them in several ways to obtain a better correlation, of course. For the updating, I have multiple approaches. So I mainly looked into the resonator. And first, of course, I have just a CAD model of my resonator, mesh it, run the analysis, use the material properties of the datasheet, and I can have a first estimation of my resonance frequency, of course. Then I also can, after production, update the density in my model to match the model mass with the mass of the real produced samples. Then I also have scaling, can do scaling. So the material datasheet provides like a shrinkage ratio, which I can use to update my model geometry to be more accurate to the real produced sample. And then again, I can update the mass density according to mass measurements. And then last, we also have Moldex. So as Tim also showed, we have dedicated injection molding software where we can incorporate all the injection molding parameters into the simulations and see what product comes out. So on Moldex, maybe a small slide on it. So what can we simulate with Moldex? So we can do the product filling, as you can see here. We can also export the shrinked/warped geometry. So we can also use that to do the resonance frequency analysis. We can also export the density distribution. So as these are dynamic equations, mass is important and is incorporated. So the density distribution can also be of interest. And also stresses can be calculated, but I did not yet look into that. So resulting stresses due to the shrinkage of the material. And what we then see in the results is that just by using the CAD geometry and the material properties of the datasheet, I see for the beams in PP that I have an error between the numerical frequency and the experimentally measured frequency of 12.5%, which is not that large. But by updating the mass density, so the model mass is the product mass, I already can have the error. So with only measuring the mass. Then by scaling the model, so use the scaled model provided by the material shrinkage, use the density from the datasheet, also the error is decreased. And if we then use both a scaled model and an updated density, we see that we have the smallest error until now, which is quite logic, because more or less measurement-driven updating steps. Then for Moldex, I also used the Moldex geometry with the density from the material supplier, and we see that the error is decreased but still quite large. Then I updated, so I updated density according to the mass measurements, and I see the smallest error of all. So we have a quite assimilated geometry and a measured density, so to say. And then the last approach is very interesting because it's purely simulation driven. What I did is the Moldex geometry, so the warp geometry from the simulations, and also the density out of the simulations. And I see again that the error is half the starting error. So this is very interesting because for this I do not need measurements, so I do not need to produce samples, and I do not need an expensive mold before I do my to see what the real performance of the metamaterial would be. Then for ABS, it's actually more or less the same, although the static error is smaller, so you can see it's only 4%. That's due to the smaller shrinkage of the material. So the CAD geometry already more or less is a good representation of the real product geometry, which is not the case for PP as it has a high shrinkage. So to wrap that up, depending on the material, we have some off-design present, but we can update it based on simulations and our measurements. But I can further look into the Moldex simulations because now these were more or less the first simulations I did, and I'm pretty sure that I can improve them and improve the error of the fully simulation-driven approach. So fast, the main conclusions. We have benchmarked that the injection molding process is a robust process in terms of product. I don't know if they hear me on the live stream, otherwise I would just talk. I do not need it, I think. And now, yeah, now it should work, I think. Yeah, so we also plan to look to simulate a bit on which parameters are the key parameters to influence the dynamic behavior of the product. So we can do that based on experiments, but I also will do it a bit with simulations to have already an idea present before starting experiments. Normally it is. I would look out for it because there are several, how to say, license packages. So we need to be sure that we have the license for that. But it is definitely. indeed. More questions? No one? Yes, I have. So that really depends actually on the application. So for example, going to go a bit back. That was enough. So here I show the stop band, which is quite a narrow band in this case. If you really would like, for some reason, a narrow band, then a small spread is already large, so to say. But if the band you target or you are creating is a bit wider, then a small spread is not that kind of a problem, so to say. So it depends a bit, but a bit of spread is actually not that problematic, because spread also broadens the stop band. But the problem is that it needs to be spread that we can predict, so to say. So we have to know what comes out of it in terms of performance. So that's basically additive manufacturing has some spread, which is not that bad, but it's really unpredictable. So that's why these simulations for injection molding come into view.
Test, test. Test, test. 1, 2. 1, 2. Hallo, hallo. Ah.
Niet. Of amper.
Hallo.
Ja.
Ah. Oké. Hoor je mij? Ja, oké, goed. All right. After these technical complications, let's go on with my presentation. So thank you for still being present. I will present to you the work I've been doing for the last year as a PhD student on femtosecond laser ablation for the creation of molds for injection molded hollow microneedles. It's a mouthful, but hopefully at the end or during this presentation, you'll understand what it's about and what the challenges are and what I'm doing. Yeah, all right. So a small part about the context of my research. My PhD is part of a IDN project, which is a big consortium of different research groups. There are research groups from Gasthuisberg that are working on the development of a vaccine that can be injected transdermally, so it means that it can be injected right under the upper layer of the skin. There's researchers from Mebius that are working on the microfluidic patch. Also, Tim showed you an example of a microfluidic patch that can be used. And Tim and we are working on the manufacturing techniques for this patch. So the goal is really to make an autonomous microfluidic patch for vaccine delivery transdermally. Then a little bit deeper into the microneedles. You have already had an introduction of microneedles from Tim. So this one will be pretty short. If you ask Wikipedia what is a microneedle, well, you'll get this definition. Microneedles are microscopic applicators that are used to deliver vaccines or other drugs across mainly the transdermal barrier. And this is true. Microneedles are usually arranged in arrays. You can see an image on the right of the screen. They're between 150 and 1,500 micrometers long, and they are about 50 to 250 micrometers wide. They have several main advantages compared to traditional needles, also called hypodermic needles. They do not require any trained personnel to be handled, so it allows self-medication. So this is a main advantage for third world countries where medical health care is really lacking. Now, they can also be made fully in plastic, as Tim showed just before, and this makes it easier for waste removal. And finally, they do not generate pain nor pain-related stress because they are not long enough to touch your nerves. Here is an image of a hollow microneedle, because also Tim showed there's a lot of sorts of microneedles, and I will focus on the hollow microneedles. These allow the injection or the extraction of more fluid due to their lumen inside. It's a little channel inside of the lumen, inside of the needle. They can be made out of silicon, metal, ceramic, or polymer. We can see pretty much everything in the literature, and they people also use various methods to produce them. And out of these methods, it's very important to find the cheapest, easiest, and fastest way to produce hollow microneedles, because this is a product that we will have to manufacture in big quantities. So this last method with femtosecond laser ablation and injection molding has been developed by Tim Evans and some colleagues, and it actually uses a super fast or ultra fast laser to take off some material, to ablate material from a mold insert. Then we place the mold insert into an injection molding machine, and finally what we get out is a polymer plate with hollow microneedles on it. This is a very promising technique, but as you'll see, here the femtosecond laser process, this is a slide I took from Tim, has a lot of different parameters that can vary, and there's a lot of parameters that we don't know the influence of on the final shape of the microneedles. Here also some slides from Tim's work from the proof of concept. You can see that by changing any parameter, let's say the position of the lumen, you get a totally different hollow microneedle shape. Also by having the same laser parameters but in just another material, another target material, well, you also get totally different hollow microneedle or solid microneedle shapes. So the big question is, how can we predict the shape of those hollow microneedle cavities? Because we need to be able to say, well, we need this shape, this geometry of the needle, we need it to be that strong and have this wall thickness, but then we need also to be able to manufacture it, to find the right laser parameters to manufacture it. And since there are so many parameters, well, there comes a model into play. But first, before I'm gonna talk really about the model, there's gonna be 1 or 2 slides explaining what is femtosecond laser ablation, because it's quite important to know why we use this such a special process. And here's a bit more context on the femtosecond laser ablation. Femtosecond laser ablation is actually the process where you shoot pulses at a material, and the pulses are shorter than the time needed for the electrons that are absorbing the energy to transfer the energy to the lattice. This is called the relaxation time. So energy, the electrons get the energy from the photons instantaneously, they give it to the lattice, but when they give it to the lattice, the pulse has already stopped. This leads to a 2-temperature state of the material and a very sudden and very precise material removal. There's no heat affected zone and also almost no molten material, and we have a vapor and plasma phase that is created. This is a very precise process, and it uses no chemicals, it's super tunable, and it tends to go towards higher and higher material removal rates as the time goes by. Yeah, the technology is just increasing. So there's a few mechanisms playing a role in femtosecond laser ablation. The main ones are incubation, fluence, decrease on the steep walls, and the reflectivity. So the incubation is actually the fact that it is easier for the second pulse to ablate material. So to remove material, it's easier for the second pulse than for the first pulse, because the first pulse will leave some extra energy, let's say, in the material, will excite the material, and it will be easier for the next pulse to ablate the material. Now, the fluence on the decrease on the steep walls is also quite important, because as you can see, this is then a possible cavity that is created by shooting multiple pulses at the same point. So percussion drilling, this is called. And imagine that with each pulse, the cavity increases in size and in depth. So also the area of the cavity will increase. And since the ablation is relative to the fluence, which is the energy density, the energy divided by the area. Since the area increases, the fluence will decrease, and the ablation per pulse will also decrease. This is quite a complicated relation when said like this, but we can compare these two first phenomena and say that the incubation factor makes it easier for the next pulse to take away material, but the fluence decrease makes it actually harder for the next pulse to take away material. So these are these phenomena are not doing the same, are doing opposite things. And then we have the reflectivity, which is dependent on the inclination of the surface, and this is this has also to be taken into account in the model. Here we have a bit of a schematic of the laser beam and the laser material interactions. We can see the laser beam, which has usually a Gaussian shape, which means that there's more energy in the center of the beam than when we go towards the sides. Some part of the energy is reflected by the internal walls or by just the material. Some part of the energy is used for incubation or excitation for the next pulse. And then we have internal wall reflections, which happens when energy, when laser rays are reflected towards the bottom of the cavity and gets concentrated there and ablate more material there than somewhere else. We have the surface area, which is growing with every pulse. We have also plasma shielding, which happens when a lot of pulses are shot at the same point consequently. And finally, evaporation or ablation. This is what we want. So we have all these side factors playing a role, but the only thing we want is this growing surface area and evaporation of the material. We have to take this all into account into these formulas that I won't really go into, but as you see, this is the ablation of the material per pulse. It's dependent on the fluence, which is the energy density, which is also dependent on some factors, and the threshold fluence, which is the minimal energy density that is required to have ablation, is also dependent on some factors. So how do we calculate the angle of incidence or the inclination of the surface? This is quite important to know, to calculate all these previous parameters. In the model, we simply take the least squares plane of all the points around the point of interest, and we calculate the angle between the normal of this plane and the propagation direction of the laser. Then the polarization angle to calculate the reflectivity, because the reflectivity is not the same for a plane that is perpendicularly polarized to the inclination direction as for a plane that is parallel polarized to the inclination direction. So for that, we take the projected normal of the least squares plane, and we take the angle between the polarization direction of the laser beam. You can see that we can split that way the beam into a parallel laser beam and perpendicular laser beam. So let's get out of this equations and phenomena talk and talk about more of the laser model, how it's built and how it gets its results. So we have some material parameters, we have laser parameters and laser strategy parameters. These are used as input for the model. In the model, those complicated equations will do the work and calculate the ablation profile for this pulse. Then finally, we add it to the total crater profile. For the first pulse, it will be just a flat surface, so we'll have the first ablation profile. We use this ablation profile as an input for the next pulse because we need the cavity shape to calculate the new ablation of this pulse. So in a more schematic way, it looks like this. So we have let's say we want to make a line of 6 pulses here on the slide. We're gonna move our laser around and shoot a pulse at every point. So we want to make line scanning. We construct a global mesh around the global ablation profile. Then we select the local mesh around the first pulse center. The model will calculate the ablation profile of this pulse. Because this is the first pulse, it's done for this pulse. For the second pulse, the center is given with the red cross always. We select the new local mesh around this new pulse. We calculate the orientation for each local mesh point. So we go through all the points in here and calculate and see the orientation so we can calculate the reflectivity and so on. And finally, we calculate the extra ablation profile and add it to the global ablation profile. And we do this for the 6 pulses, and then we have eventually the total profile, the total cavity that we have created with the femtosecond laser. So this is the approach I want to do. I want to use to predict the microneedle cavities, but this model needs to be validated. First, I'm gonna validate it for the simple laser strategies. The most simple laser strategy being percussion drilling, while all the pulses are shot at the same point on the target material. Then lines and grooves, which are always parallel lines. And finally, those very complicated laser scanning strategy for microneedle cavities and hollow microneedle cavities. So for percussion drilling, these are the first results that I got. I tried to model the percussion drilling experiments, and what I got in the beginning was this orange line. And this orange line you actually get when a mesh point is coincident with the laser beam center. And this creates actually an irregularity in the calculations, in the mathematics. It creates a jump in ablation rate. So you want to avoid this and create your mesh around the laser beam center so that the mesh finally converges towards the final shape. These are sections of actual 3D shapes that I constructed. Yeah, we can also see that the laser, that the simulations converge towards some value, and you need more mesh points to make your simulations converge when the laser beam radius is smaller than for when the laser beam radius is larger. This just has to do with the profile of the laser fluence. Then I wanted to validate my model for percussion drilling against the literature and against experiments. But in the literature, I couldn't find any well-documented percussion drilling experiments. So I went over to laser scanning in the literature. So this laser scanning is basically when you make a line with the laser, like the example I showed you, but you go a few times over that line to make it more and more clear that you are ablating, because you ablate only a very, very small amount per line. And in the literature, they tried also to model this, but only in 2 dimensions, so they don't take everything into account, and eventually they even tweaked their model to make it fit these experiments. But yeah, I said, you know what, let's go for it. I just take the material parameters from the literature, from other books. I take the laser parameters that they use in the paper. I modeled the 3-dimensional model, and here are the sections. They look pretty identical or pretty similar to the sections above, so this is a very promising result. Of course, it's not enough to validate the model, so I designed my own set of experiments in which I vary a lot of things. I vary the number of pulses, I vary the repetition rate, which is a laser parameter, and I vary the fluence, which is the energy density. And with wire EDM and nano CT, I finally could characterize a few of these experiments. And here is here's an image of the nano CT image that you can get with these experiments. And you can see that with a changing number of pulses, the depth is quite similar between the simulations and the experiments. I didn't have time as of yet to characterize the other experiments, but I'm very excited to see if the correlation will hold on for the other variations. Overall, the advantages of this model, even if it's not fully validated yet, it still looks very promising, and with every new step, it looks even more promising. It's a 3-dimensional model, and so the reflectivity and the area factor are completely included, which is something you cannot do in a two-dimensional model. And also the pulse by pulse approach allows us to predict any laser scanning strategy that we want. So let's say we want to do something else than hollow microneedles. Next time, let's say we want to do pyramids or hierarchical structures. Well, we still can do it with this model as long as we're not looking into the nano range or too small or too big. So these are the next tasks I want to do with this femtosecond laser model. First, I want to validate the model with still some simple and even going to more complicated laser scanning strategies. Then I want to optimize the model for speed and ease of use. This is already going, and it's in collaboration with Steins Schildermans. And finally, I want to validate the model for other metals that are very widely used in the injection molding industry, such as copper alloys or aluminum. Thank you very much for your attention and for staying to the end. And if you have questions, please ask. For now, since there's no actual result of the validation, I can't say what is good or what isn't good enough. But with the speeding up of the model, it gets easier and easier to predict very time expensive, let's say, laser strategies such as the cross-hatching of microneedles. So since this is easier to do, I want to go as fast as possible towards these difficult strategies and see, for example, the link between the correlation of the models in the percussion drilling and the results in the models with a lot of pulses. Yeah. Yes, so I don't take this into account. This is the next thing I will take into account if I have to modify my model because the results aren't good enough. But for now, why I didn't take it into account and I want to test it like this is actually because we assume now that the result of this internal wall reflection is actually a very, very narrow channel just at the bottom of the microneedle cavity. So we have the microneedle cavity, which has a range of, like, let's say a few hundreds of micrometers, a tip radius of a few micrometers, and then even smaller than that, 1 micrometer or something, there's a very narrow channel that we can see in the experiments that Tim did. And this channel barely even gets filled with polymers. So for this application, it wouldn't be useful to predict this channel also. And aluminum? Yes, so for different target materials, we are looking at different material parameters, and there will be a difference in the reflectivity and the threshold fluence. The incubation factor is pretty much the same for every metal, and the penetration depth is also relatively the same for a wide range of metals, let's say. But I intend to see a difference in the threshold fluence and in the reflectivity. Yeah. yeah, that is what I think, but it still has to be investigated. I haven't tried this model on other materials yet. This is on my planning. For aluminum and copper alloy, no, I don't know. Now this it's also aluminum will be quite easy to find, I think, but copper alloy is a little bit more tricky, as this to find in the literature. But no, I have no idea. Is there any other question? Yeah. Yeah. So it's true. The incubation makes it easier for the next pulse to ablate than the first pulse, but yeah, and also the time is important. There are in the literature again some people who say it is very important, should be taken into account, but most people agree on the fact that it is not, as long as you stay in the fact of a few kilohertz. So as long as the pulses do not are not so far away from each other that the heat is completely gone. Now, of course, if you're doing this complicated laser strategy and then 3 seconds after or even half a second after you come back on the same point, then this will not be taken into account as incubation. Then you just start from 0 again. All right, I think that's it. Have a good evening.